The universe, a vast, mysterious realm where incomprehensible forces relentlessly shape the very fabric of reality. It is a place where the fundamental laws of physics themselves bend and twist into mind-boggling anomalies, defying our deepest understanding. From the captivating dance of black holes to the eerie silence of cold, lifeless worlds, the universe continues to astonish and challenge us in ways we never thought possible. Each corner of space hides secrets that demand exploration. Join us as we venture into the most horrifying anomalies of our universe and search for answers to some of the biggest questions that have perplexed humankind for centuries. One of the most compelling phenomena in the universe are black holes, enigmatic objects that have captured the imagination of scientists and the public alike. These cosmic giants are defined primarily by their overwhelmingly strong gravitational pull. This immense gravity arises from a singularity, a point in space where an extraordinary amount of mass has been compressed into an incredibly small volume. The gravitational force exerted by a black hole is so powerful that not even light, something that travels at the fastest speed known to humankind, can escape its grasp. This is why they are aptly named black holes. The inability of light to escape means these objects remain invisible, detectable only through indirect methods such as the behavior of nearby stars or the radiation emitted as matter is pulled in and swirled around the event horizon. There are several types of black holes, each with its own unique characteristics. Stellar black holes are the most common, formed from the remnants of massive stars that have gone through supernova explosions. These colossal explosions occur when a star has burned through its nuclear fuel and can no longer support its own gravity. What remains after the explosion is a dense core, which eventually collapses into a black hole. On the other hand, supermassive black holes reside at the centers of galaxies, including our very own Milky Way. These giants can have masses ranging from millions to billions of times that of our Sun. Their growth is a slow and voracious process, likely taking place over billions of years as they accumulate matter, merge with other black holes, and continue to grow without limit. Their sheer size and insatiable appetite for matter exemplify the terrifying power they wield. Perhaps one of the most fascinating aspects of black holes is their ability to warp space and time. According to Einstein's theory of general relativity, space and time are not rigid, unchanging entities. Instead, they can be bent and stretched by massive objects, especially black holes. Near the event horizon of a black hole, the very fabric of space-time is so distorted that time behaves in a strange, almost alien way. For an observer far from the black hole, time appears to slow dramatically as they approach the event horizon, a phenomenon known as time dilation. This presents an extraordinary perspective on the nature of time itself. What might seem like seconds for a person near the black hole could stretch into hours, days, or even years for someone far away. Furthermore, black holes exhibit another strange and awe-inspiring property: Hawking radiation. First theorized by physicist Stephen Hawking, this radiation suggests that black holes are not eternal, as once thought. Instead, they could gradually lose mass over time by emitting radiation, leading them to eventually evaporate. This raises profound questions about the nature of black holes and the information they consume. What happens to the information that falls into a black hole? Does it disappear, or could it be stored in some other form? The mysteries surrounding black holes continue to baffle scientists as we strive to understand their true nature. But black holes are not the only astronomical entities that present challenges to our understanding of the universe. Neutron stars, another extraordinary class of celestial objects, also push the boundaries of what we know about matter, gravity, and the fundamental forces that govern the cosmos. These stellar remnants are born from the collapse of massive stars that have exhausted their nuclear fuel, leaving behind an incredibly dense core. The density of a neutron star is so extreme that just a single cubic centimeter of neutron star material would weigh approximately as much as all of humanity combined. To put this into perspective, imagine squeezing the mass of an entire city into the size of a sugar cube. This immense density creates a state of matter unlike anything we encounter on Earth. In a neutron star, the pressure is so intense that it forces the protons and electrons within atoms to combine, forming neutrons. This creates a new form of matter, often referred to as neutronium, that exists only under such extreme conditions. This exotic state of matter raises a host of questions about how particles behave when squeezed together under such crushing pressure. How are neutrons packed so tightly? How does this matter interact with other types of matter? And what do these strange conditions reveal about the fundamental forces that govern our universe? The study of neutron stars presents a unique opportunity to investigate the very building blocks of the universe. The behaviors of matter under these extreme conditions might offer clues about the forces that control everything from subatomic particles to galaxies. Furthermore, the interactions between the dense matter of a neutron star and the powerful gravitational forces at play could provide valuable insights into the nature of gravity itself, a force that, despite its omnipresence, remains poorly understood in many respects. The universe, in all its mystery and wonder, continues to reveal new and unexpected anomalies that challenge our comprehension of reality. Whether it's the mind-bending behavior of black holes or the enigmatic nature of neutron stars, we are constantly reminded that our understanding of the cosmos is far from complete. As we continue to explore these extraordinary phenomena, we come closer to unlocking the deepest secrets of the universe, seeking answers to the questions that have intrigued humanity for millennia. And perhaps in the process, we will discover even more incredible mysteries waiting to be uncovered in the infinite expanse of space. Neutron stars, among the most fascinating and extreme objects in the cosmos, serve as natural laboratories where the most extreme gravitational phenomena unfold. These stellar remnants, with their intense gravitational fields, provide a unique testing ground for Einstein's theory of general relativity. Their extraordinary gravitational forces offer an unparalleled opportunity to study how gravity behaves under conditions far beyond anything we can replicate on Earth. One of the most significant ways these stars allow us to explore gravity is through the observation of gravitational waves, ripples in the fabric of space-time that travel outward from merging neutron stars. These waves carry crucial information about the interactions between objects with massive gravitational influence, and they provide concrete evidence about the nature of gravity in the most extreme environments. By examining such waves, scientists can test theoretical models of gravity, refining and adjusting our understanding of the fundamental forces that govern the universe. Neutron stars also pose profound questions about the nature of matter itself. Researchers are keen to explore the limits of matter's stability and to uncover the complex processes that lead to the formation of these compact objects. Each new discovery in neutron star research pushes the boundaries of knowledge, not only deepening our understanding of the universe's fabric, but also challenging our fundamental perceptions of how matter and gravity work within the grand scale of the cosmos. Among the most captivating objects in the universe are pulsars, rotating neutron stars with incredibly strong magnetic fields. These celestial bodies emit powerful beams of electromagnetic radiation, which are directed along their magnetic poles. As the pulsar spins, these beams sweep across the cosmos like the light of a lighthouse. When Earth happens to lie in the path of these beams, we observe them as regular pulses of radio waves, hence the term pulsar. Pulsars are particularly intriguing because of their astonishing rotational speed. Some pulsars rotate several hundred times per second, producing pulses that are extraordinarily precise. This level of consistency allows scientists to use pulsars as cosmic clocks, offering a reliable method for measuring time and space. Their timing is so precise that variations in their pulses can be measured to less than a millisecond over thousands of years, making them one of the most accurate natural timepieces known to science. This level of precision opens the door to a deeper understanding of fundamental physical principles such as gravity, space-time curvature, and the effects of these forces at cosmic scales. Moreover, pulsar signals carry valuable information about the medium that exists between the stars, the interstellar medium. As these radio waves travel through space, they can be delayed or scattered by particles and magnetic fields in the intervening matter, providing insight into the density and structure of the material between stars. By studying these subtle variations in the signals, Astronomers can map the distribution of cosmic matter, revealing the composition and structure of our galaxy in unprecedented detail. Pulsars also play a vital role in testing the theories of physics under extreme conditions. Particularly in binary systems where a pulsar pairs with another star, pulsars offer a unique opportunity to observe gravitational waves and test Einstein's general theory of relativity. The ongoing study of pulsars continues to reveal new and exciting insights into the workings of the universe, offering a window into the deepest mysteries of cosmic phenomena. Supernovae, the explosive deaths of massive stars, are among the most dramatic and awe-inspiring events in the universe. When a star exhausts its nuclear fuel, it can no longer support its own weight, leading to a catastrophic collapse. This collapse triggers an explosion so powerful it briefly outshines entire galaxies. Supernovae are crucial to understanding the life cycles of stars and the processes that govern their evolution. These stellar explosions provide essential clues about the star's composition, mass, and age, and they play a key role in the larger dynamics of the cosmos. There are two primary types of supernovae, Type 1 and Type 2. Type 1 supernovae generally result from the merger of white dwarf stars, while Type 2 supernovae occur when a massive star reaches the end of its life and succumbs to gravitational collapse. By studying these two types and their distinct characteristics, astronomers can trace the life histories of the progenitor stars, learning more about their mass, age, and evolutionary pathways. Supernovae are not just spectacular displays of stellar death. They are essential to the creation and distribution of heavy elements throughout the universe. In the explosive aftermath of a supernova, elements such as carbon, oxygen, and iron, which were forged during the star's lifetime, are blasted into space. These elements enrich the interstellar medium, providing the raw materials for the formation of new stars, planets, and potentially life. Without supernovae, the chemical building blocks necessary for planets and life as we know it would be vastly less abundant. Furthermore, supernovae serve as valuable tools for measuring distances across the cosmos. Type 1a supernovae in particular have a remarkably consistent luminosity, which makes them excellent standard candles for gauging the distances to far-off galaxies. By observing these explosions in distant galaxies, astronomers can calibrate their measurements and gain a more accurate understanding of the expansion of the universe. In essence, supernovae are not merely the violent deaths of stars. They are the engines that drive the cosmic cycle of matter, enriching the universe and providing critical insights into the ongoing evolution of the cosmos. Fast radio bursts, or FRBs, are some of the most mysterious and powerful phenomena in the universe. These brief but intensely energetic bursts of radio waves were first discovered in 2007, and their origins remain largely unknown. Each burst lasts only a fraction of a second, yet they can release as much energy as the sun emits over an entire day, compressed into a mere millisecond. Despite their fleeting nature, FRBs have captivated the attention of astronomers worldwide, sparking a wave of research aimed at uncovering their origins. One leading hypothesis suggests that FRBs could be caused by magnetars, neutron stars with an exceptionally strong magnetic field. These magnetized stars may release bursts of energy from their intense magnetic activity, creating the conditions for these powerful radio waves to escape. Another possibility is that the bursts result from the violent interactions between neutron stars or black holes. These catastrophic collisions could release enormous amounts of energy, including electromagnetic radiation, such as radio waves. FRBs, while still largely enigmatic, provide a powerful avenue for investigating some of the most extreme conditions in the universe. Their study could unlock new understanding about the fundamental forces and objects that shape the cosmos, and they may ultimately shed light on one of the greatest mysteries of modern astrophysics. In the vast expanse of the cosmos, some researchers have proposed more extraordinary theories to explain the phenomena known as fast radio bursts, FRBs, suggesting that these intense, brief bursts of radio waves could be linked to advanced extraterrestrial civilizations utilizing highly sophisticated energy sources for communication. While this hypothesis remains speculative and far from proven, it undeniably adds an exciting and provocative layer to the search for FRBs. Given the immense size of the universe, combined with the countless unknowns we face in space exploration, the idea that these mysterious bursts might be signals from distant civilizations adds an element of adventure to the ongoing quest. As scientists continue to scrutinize data and gather evidence, our understanding of these elusive bursts is gradually taking shape. Each discovery, no matter how small, provides new insights into the workings of the universe, shining light on phenomena we once thought were beyond our comprehension. It is as if every breakthrough pulls back another curtain on the cosmos, revealing just a little more about the vast and complex web of energy and matter that makes up our universe. But perhaps more intriguing is how each new revelation about FRBs pushes us to reflect on larger existential questions, such as the very nature of the universe itself. What if these bursts were not just signals, but markers of something far greater that lies beyond our grasp? In some sense, the search for answers about FRBs is a journey that may forever alter how we view our place in the cosmos. Much like the search for extraterrestrial life, it calls us to question not only what we know, but also what we think we know, stretching the boundaries of our understanding and forcing us to reconsider the fundamental rules that govern the universe. Among the most enigmatic objects that help us navigate the cosmos are quasars. These fascinating astronomical phenomena are some of the brightest and most energetic sources of light in the universe. Powered by supermassive black holes at the centers of distant galaxies, quasars act as cosmic beacons, lighting the way for astronomers to peer deep into the early universe. When matter falls into a supermassive black hole, it accelerates and heats up, releasing tremendous amounts of energy that can be observed across unfathomable distances. Some of the light we observe from quasars today has been traveling through space for billions of years, providing us with a glimpse of the universe in its infancy, long before Earth or even the solar system came into being. One of the most profound contributions of quasars to our understanding of the early universe is their role in tracing the evolution of galaxies. By studying the light emitted from these distant objects, scientists are able to gather invaluable data about the intergalactic medium, the vast space that exists between galaxies. This seemingly empty void was anything but empty in the early universe. It was a dynamic, ever-changing environment that underwent drastic transformations as the universe cooled after the Big Bang. Quasars, with their blinding brightness, serve as tools to probe this primordial medium, allowing researchers to gain insight into the conditions that existed long before the formation of galaxies and stars. When light from a quasar passes through the gas and dust on its journey to Earth, it interacts with these materials in ways that leave behind distinct imprints. These imprints, like fingerprints, can be studied to reveal the properties of the early universe and the forces that shaped its development. The information gathered from quasars has helped scientists understand how the universe transitioned from a dense, hot plasma to the cooler, more structured system we see today. Moreover, quasars serve as valuable markers for locating distant galaxies. Their extreme brightness allows astronomers to detect them even when they are billions of light years away. By pinpointing the location of quasars and studying their light, researchers can map the large-scale structures of the universe, tracking how galaxies have evolved and distributed themselves over time. This process helps us understand how galaxies formed, how stars were born, and how these processes shape the fabric of the universe itself. In a larger sense, quasars provide us with a unique window into the past, offering clues about the formation and evolution of the cosmos over billions of years. The study of these remarkable objects suggests that black holes began to play a significant role in shaping the universe nearly as soon as the first stars were born. This raises intriguing questions about the relationship between black holes and galaxy formation, questions that scientists are still working to answer. Through the study of quasars, we not only learn more about the early universe, but also gain insight into the fundamental processes that have shaped our cosmic home. Equally mysterious and integral to the structure of the universe is dark matter, a substance that exerts a gravitational influence on galaxies but remains invisible to our current instruments. Dark matter is believed to account for about 27% of the universe's total mass, while ordinary matter, Everything we can see, from stars to planets, makes up only around 5%. Despite being invisible, dark matter plays a crucial role in the formation and evolution of galaxies, acting as a sort of scaffolding that organizes visible matter. Without dark matter, the galaxies we observe today might never have formed as they did. In the aftermath of the Big Bang, tiny fluctuations in the density of matter and energy set the stage for the formation of galaxies. These fluctuations were more pronounced in regions dense with dark matter, which began to clump together under the influence of gravity. As dark matter formed halos, vast, invisible structures, it provided the necessary gravitational pull to gather gas and dust, ultimately leading to the formation of stars and galaxies. As galaxies continued to evolve, dark matter remained integral to their growth. Observations of spiral galaxies, for instance, reveal that their stars rotate at speeds that cannot be accounted for by the visible matter alone. Dark matter, in its unseen yet profound influence, accounts for this discrepancy, providing the additional mass needed to keep the galaxies intact. In this way, dark matter not only shapes the individual structure of galaxies, but also influences the formation of clusters of galaxies, ensuring that these cosmic structures remain bound together through gravitational attraction. Thus, dark matter acts as the unseen architect of the universe, shaping the very structure of space itself. While we cannot see it, its gravitational effects are felt throughout the cosmos, guiding the creation of stars, galaxies, and the large-scale structures that make up the universe. As we continue to search for a deeper understanding of this mysterious substance, we are reminded of the limits of our knowledge and the vast expanse of the unknown that still remains beyond our reach. Dark matter holds a mysterious yet profound influence on the universe's large-scale structure, shaping the very backbone of the cosmos. It's not just something we can study indirectly. It plays a crucial role in the formation of vast cosmic webs, intricate structures that connect clusters of galaxies, bridging the seemingly endless stretches of nothingness between them. These cosmic webs act as the architecture of the universe, their connections forming the skeleton around which galaxies are strung, and their influence extends to vast, empty voids that span between these galactic islands. Although our understanding of dark matter remains elusive, its gravitational effects provide a powerful window into the hidden workings of the universe. We may never fully comprehend its nature, but its existence and impact offer us invaluable clues about the mechanisms governing cosmic behavior. Through dark matter's interaction with normal matter, we catch glimpses of the beautiful complexity woven into the cosmic dance of creation, destruction, and ongoing evolution. It's an ever-unfolding mystery, urging us to delve deeper, pushing us to unravel the very fabric of existence itself. In the midst of this exploration, we also encounter another tantalizing concept: cosmic strings. These are theoretical objects that emerge from the earliest moments of the universe's birth, proposed as one-dimensional defects in the very fabric of space-time. Imagine them as impossibly thin yet infinitely long threads that stretch across the universe, often likened to slivers that run parallel to the vast expanse of the cosmos. They are born from phase transitions, similar to how defects form when water freezes into ice. But at the cosmic scale, these transitions occur under the extreme conditions of the early universe. Though cosmic strings remain a theoretical idea, their implications are profound. It's believed that they could exert tremendous gravitational forces, creating distortions in the space-time continuum that mirror the behavior of massive celestial bodies like stars or planets. If these strings indeed exist, they could warp the very fabric of space-time around them, potentially altering the trajectories of light and matter in dramatic and observable ways. Imagine light passing near such a string. It could bend around it, creating a phenomenon similar to gravitational lensing, where the light is distorted and magnified as it passes through the intense curvature. This could give rise to observable patterns in the sky, clues that might one day reveal the existence of cosmic strings, even if we cannot directly see them with our current tools. The potential effects of cosmic strings stretch far beyond their gravitational impact. They challenge our understanding of the fundamental forces that govern the universe, as well as the very conditions that existed in the moments following the Big Bang. What can the existence of these strings tell us about the conditions of the early universe? How might they have influenced the growth and structure of the cosmos as we know it today? These questions open up exciting avenues for further research, offering a glimpse into the origins of cosmic evolution. If we can unlock the mysteries of cosmic strings, we might uncover insights into the nature of space-time, the forces that shaped our universe, and the conditions that gave rise to the cosmos we see unfolding before us. Cosmic phenomena continue to captivate our imagination, offering tantalizing glimpses into the fabric of the universe that lies just beyond our understanding. Among these phenomena, cosmic strings stand out as particularly intriguing. If they do indeed exist, cosmic strings could unlock explanations for certain anomalies observed in the cosmic microwave background radiation, often referred to as the afterglow of the Big Bang. This radiation is a faint echo of the birth of the universe itself, and understanding cosmic strings could provide a crucial link between various concepts in theoretical physics, including string theory and quantum mechanics. In a sense, cosmic strings would invite us to think of the universe as an intricate tapestry, woven from threads of matter, energy, and space-time, all interacting in ways we are only beginning to grasp. The investigation of these celestial phenomena doesn't just connect us to our cosmic origins, it also holds the potential to reveal deeper laws that govern the cosmos, laws that stretch far beyond our current comprehension. The more we explore, the more we are left with a sense of awe and wonder at the vast mysteries that surround us. In the search for new frontiers, the discovery of exoplanets, the planets that orbit stars outside our solar system, has become a groundbreaking pursuit. These exoplanets come in a dazzling array of forms, each with its own unique characteristics, offering clues about the forces that shape planetary systems. The primary categories of exoplanets include gas giants, rocky worlds, icy planets, and an especially fascinating group called super-Earths. Gas giants, much like our own Jupiter and Saturn, are massive planets predominantly composed of hydrogen and helium. These gas giants are typically devoid of solid surfaces, characterized by thick atmospheres and extreme conditions that make them vastly different from terrestrial planets. Studying gas giants allows scientists to explore the dynamics of planetary atmospheres, magnetic fields, and weather systems. In fact, some of the storms found on gas giants are so immense that they far surpass anything we experience here on Earth. The more we learn about these planets, the clearer it becomes that their study helps us understand not only the planets themselves, but also the complex processes that lead to their formation. On the other side of the spectrum, rocky planets like Earth are of paramount importance to astronomers, primarily because they hold the potential to support life. Finding planets that have conditions similar to Earth's, especially those situated within a star's habitable zone where liquid water could exist, is a key objective in the search for alien life. Studying the formation and evolution of these rocky planets provides valuable insights into our own planet's history, shedding light on the factors that might contribute to the emergence of life elsewhere in the cosmos. Yet, there is another category of exoplanet that has been garnering attention: the super-Earths. These planets, which are larger than Earth but smaller than Neptune, represent a unique intersection of rocky and gas giant characteristics. Some of them may have thick atmospheres or even oceans, suggesting the potential for diverse environments. Super-Earths challenge our assumptions about habitability and broaden our questions about the possibilities of life beyond Earth. As we venture deeper into this uncharted territory, we continue to expand our understanding of the universe and our place within it, realizing that we are only scratching the surface of what lies beyond our solar system. Gravitational waves, ripples in the very fabric of space-time, are another profound discovery that has revolutionized our understanding of the universe. These waves are generated by the most violent and energetic events in the cosmos, such as when black holes or neutron stars collide or accelerate. To conceptualize this, imagine throwing a stone into a calm pond. The ripples that spread outward from the point of impact are analogous to gravitational waves. First predicted by Albert Einstein as part of his general theory of relativity more than a century ago, gravitational waves remained theoretical until their first detection in September 2015. This breakthrough was made possible by the Laser Interferometer Gravitational Wave Observatory, LIGO, a joint project involving scientists from the United States. The discovery of gravitational waves marked a pivotal moment in astrophysics, providing direct proof for a phenomenon that had once existed only in the realm of theory. It revealed a universe more dynamic and interconnected than we had ever imagined, allowing us to observe cosmic events that were previously invisible to conventional telescopes. This new field of observation, known as gravitational wave astronomy, has opened a window into phenomena like black hole mergers and neutron star collisions, events that often remain undetected by light. By studying the waveforms created by these events, scientists can learn about the mass, spin, and distance of celestial objects, helping to refine our understanding of the structure and evolution of the universe. But the implications of gravitational wave research go far beyond merely satisfying cosmic curiosity. These waves hold the key to answering fundamental questions about gravity, the behavior of matter under extreme conditions, and even the origins of the universe itself. Each detection reveals new layers of understanding, gradually pulling back the veil on the universe's mysteries and presenting a more intricate, interconnected view of the cosmos. Rogue planets, celestial bodies that wander through space unbound by any star, add another layer of complexity to our understanding of planetary systems. Unlike planets that orbit a star and are part of a solar system, rogue planets have either been ejected from their original systems or never formed within one in the first place. These solitary wanderers drift through the vast expanse of space, free from the gravitational pull of nearby stars. Rogue planets can vary in size and composition, just like other planets. They might be massive gas giants or smaller, rocky worlds. What makes them especially fascinating is their isolation and the mystery surrounding their origins. Some rogue planets are thought to be remnants of star systems that underwent violent gravitational interactions, leading to their expulsion. Others may have formed in regions of space where stars were born but never settled into a stable orbit around a star. Estimates suggest that there could be more rogue planets in our galaxy than there are stars, indicating a vast population of these enigmatic objects. Many remain undetected, as they are not illuminated by the light of a nearby star. Their surface temperatures can drop to extreme lows, as they lack the warmth provided by a stellar companion. Despite the challenges involved in studying rogue planets, astronomers are keen to learn more about these elusive bodies. Studying them can offer insights into planetary formation and the dynamics of celestial mechanics. More importantly, rogue planets challenge our understanding of what it means to be a planet. Their existence underscores the complexity of cosmic phenomena and provides a window into the broader history of our galaxy. Each rogue planet tells a story of cosmic upheaval, of star systems that have either fallen apart or never truly formed. The Great Attractor, a massive gravitational anomaly located at the center of our galaxy and several neighboring galaxies, plays a pivotal role in shaping our understanding of galactic movement. This enigmatic force appears to draw entire galaxies, including our own Milky Way, toward it. The Great Attractor's influence suggests that there is more mass in this region than we can detect, much of it likely composed of dark matter. What makes the Great Attractor so compelling is its profound impact on the motion of galaxies. As galaxies travel through the universe, their movement is not random. It is guided by the gravitational pull of massive structures like the Great Attractor. This colossal entity explains the peculiar motion of galaxies, which seem to cluster together, forming a cosmic network shaped by unseen forces. The Great Attractor is part of the Laniakea supercluster, a vast structure that spans over 100 million light-years and contains millions of galaxies, including our own. The discovery of this supercluster has deepened our understanding of the interconnectedness of galaxies, emphasizing that they are not isolated objects, but parts of a much larger dynamic system. Studying the Great Attractor is crucial for cosmologists. It offers vital insights into the distribution of dark matter, the large-scale structure of the universe, and the forces that drive galactic movement. With each new discovery related to this region, our understanding of cosmic evolution becomes more refined, and the true nature of the universe gradually reveals itself. Finally, the concept of dark energy has fundamentally altered our view of the universe's expansion. For much of the 20th century, scientists believed that gravity would eventually slow the universe's expansion, a process that began with the Big Bang. However, the discovery of dark energy, an enigmatic force that seems to accelerate the universe's expansion, has forced astronomers to rethink their understanding of the cosmos. As we continue to probe the mysteries of dark energy, we may find that it holds the key to some of the most profound questions about the nature of the universe itself. In the late 1990s, an extraordinary revelation shook the foundations of modern cosmology. Observations from distant supernovae, those stellar explosions that light up the heavens, uncovered something that defied all expectations. Instead of the universe's expansion slowing down, as previously thought, it was accelerating. This revelation suggested the presence of a mysterious force acting contrary to gravity, a force we came to know as dark energy. Dark energy constitutes about 70% of the total energy content of the universe, and its effects are far-reaching. Unlike gravity, which pulls objects toward each other, dark energy pushes galaxies apart, causing them to drift away from one another at an ever-increasing rate. The very notion that a force of such power exists, exerting influence on cosmic scales, challenges everything we once thought we knew about the nature of the universe. It implies that the cosmos is far more dynamic and complex than we had ever imagined. The consequences of this accelerated expansion are profound. If the current rate continues, it suggests that the universe's future is not merely about galaxies growing increasingly distant from one another. Instead, it may lead to a big freeze scenario, a state in which galaxies, stars, and eventually all cosmic structures drift apart, isolated in an eternally expanding universe. In such a scenario, the universe would eventually become a cold, dark expanse, with galaxies, stars, and planets slowly fading into oblivion. Yet, despite its profound effects, dark energy remains an enigma. What exactly is this force? Its properties are still unknown, and a variety of theories have been proposed to explain its existence. Some scientists suggest it could be a cosmological constant, a concept introduced by Albert Einstein, representing the energy inherent in the vacuum of space itself. Others propose that it may result from modifications to gravity at cosmic scales, an idea that would drastically reshape our understanding of fundamental physics. Despite the advancement of technology, the true nature of dark energy remains one of the greatest puzzles in contemporary science. To unravel this mystery, astronomers and physicists are turning to cutting-edge technology and advanced telescopes, which allow us to peer deeper into the universe than ever before. Every new discovery brings us a step closer to understanding dark energy, and by extension, the very principles that govern the cosmos. In this ongoing quest, dark energy not only challenges our current scientific paradigms, but also pushes the boundaries of our imagination, compelling us to reconsider our place in the vast, ever-expanding universe. However, the universe has more to offer than dark energy. A seemingly insignificant yet incredibly valuable component of the cosmos is cosmic dust. Often overlooked, this fine microscopic material plays a critical role in understanding the history and evolution of the universe. Composed of particles from stars, comets, and other celestial events, cosmic dust is a time capsule, preserving the chemical signatures of the processes that gave it birth. It holds invaluable clues about how galaxies formed and evolved across billions of years. As stars reach the end of their life cycles, they often expel vast amounts of material into space. This ejected material includes gases as well as heavier elements created through nuclear fusion. These elements interact, mixing in the cold expanse of space, eventually forming cosmic dust. This dust then contributes to the formation of new stars, planets, and even entire solar systems. By analyzing this dust, astronomers can reconstruct the types of galaxies that existed in the past and explore their role in the broader dynamics of the universe. Cosmic dust also provides insight into the environmental conditions that prevailed at different epochs in cosmic history. For instance, the dust surrounding distant galaxies tells us about the early universe, the temperature, the density, and the types of elements that were present at that time. With this knowledge, scientists can piece together a timeline of cosmic evolution, charting the transformation of the universe from the hot, dense state of the Big Bang to the vast, structured cosmos we see today. In a more profound sense, cosmic dust plays an essential role in the ongoing cycle of creation. It is the raw material from which new stars and planetary systems emerge. This continuous cycle of destruction and creation underscores the dynamic nature of the universe. Each grain of dust serves as a reminder that the cosmos is in constant flux, with the death of one generation of stars giving rise to the birth of another. Moving closer to home, the ice giants, Uranus and Neptune, hold a distinctive position in our solar system. These planets, unlike the gas giants Jupiter and Saturn, are composed largely of ices, such as water, ammonia, and methane, in addition to rock and metal. This unique composition gives them different atmospheric and physical properties, setting them apart from their larger counterparts. One of the most striking features of these ice giants is their extreme weather systems. Despite their distance from the Sun, Uranus and Neptune experience some of the most powerful winds in the solar system. Neptune, for instance, has wind speeds that can exceed 1,500 meters per second, faster than the speed of sound on Earth. The weather patterns on these planets remain enigmatic, with the exact processes that govern their violent climates still unclear. In addition to their tempestuous atmospheres, both Uranus and Neptune have unusual internal structures. It is believed that their interiors consist of slushy mixtures of water, ammonia, and other substances embedded within layers of rock and metal. This composition contributes to their extremely low temperatures and unusual magnetic fields. These fields are tilted at odd angles, unlike those of Earth or Jupiter, suggesting that something complex and dynamic is at work beneath their icy clouds. The striking blue and turquoise colors of these planets are another fascinating feature. The distinctive hues are a result of methane in their atmospheres, which absorbs red light and reflects blue and green wavelengths. This visual characteristic not only makes them mesmerizing to observe, but also points to the presence of gases that differentiate them from other planets in our solar system. Together, these remarkable properties make the ice giants subjects of continuous fascination and exploration in modern astronomy. Finally, the elusive nature of antimatter has captivated the minds of physicists and astronomers alike. Antimatter is essentially the opposite of ordinary matter, particles that have the same mass as their counterparts in the matter world, but carry opposite electric charges. For example, while an electron is negatively charged, its antimatter counterpart, the positron, carries a positive charge. Despite its intriguing nature, antimatter is incredibly rare in the universe, raising the question of how we might study it. To explore this phenomenon, astronomers have turned to the study of cosmic rays, high-energy particles that travel through space. When these cosmic rays collide with atoms in Earth's atmosphere, they can produce secondary particles, including positrons. By examining the energy and distribution of these particles, scientists can learn more about the processes that create antimatter in the far reaches of space. Another essential tool in this research is the observation of gamma rays. When matter and antimatter collide, they annihilate one another in a burst of energy, releasing gamma rays in the process. Instruments like the Fermi Gamma Ray Space Telescope are designed to detect these elusive rays, providing vital information about regions of space where antimatter may exist, such as around black holes, neutron stars, and supernova remnants. On Earth, experiments at facilities like CERN, the European Organization for Nuclear Research, are crucial for understanding antimatter. By creating controlled environments where antimatter can be produced, scientists are able to study its properties in detail. Comparing the behavior of matter and antimatter under various conditions could eventually unlock some of the deepest mysteries of physics, shedding light on why our universe seems to be made almost entirely of matter, with very little antimatter present. The exploration of antimatter, cosmic dust, dark energy, and the mysterious ice giants exemplifies the grandeur of our ongoing journey to understand the cosmos. Each discovery, each puzzle solved, takes us one step closer to answering the profound questions about the origins, evolution, and ultimate fate of the universe. The quest is far from over, and as technology advances, the mysteries of the universe will continue to unfold before us, revealing the incredible complexity of the cosmos we call home. The discovery of massive clusters of galaxies, known as galaxy superclusters, has fundamentally reshaped our understanding of the universe, offering new insights into the very fabric of the cosmos. These immense structures, composed of thousands of individual galaxies, force us to rethink the very nature of cosmic organization and the interconnectedness of matter across vast distances. As we peer deeper into these superclusters, we begin to uncover a complex network of cosmic threads, revealing a web of galaxies that stretches across the universe like a cosmic spider's web. This realization shifts the paradigm of how galaxies are distributed, showing that they are not scattered randomly throughout space, but instead form intricate patterns resembling colossal filaments. Superclusters are not only vast in size, but also crucial in advancing our knowledge of the universe's most mysterious components: dark matter and dark energy. Dark matter, an invisible substance that does not emit light or energy, constitutes a substantial portion of the universe's mass. While it cannot be directly observed, scientists have inferred its existence by studying the behavior of galaxies within these superclusters. By observing the gravitational interactions between galaxies, researchers can detect the invisible influence of dark matter, which pulls on visible matter, shaping the structure of the universe. Dark energy, another enigmatic force, is thought to be driving the accelerated expansion of the universe. It behaves like a cosmic engine, pushing galaxies farther apart over time, accelerating the expansion process. As scientists explore these superclusters, they are presented with unique opportunities to investigate the properties of dark energy. By mapping the distribution and behavior of these vast galactic systems, astronomers can gain crucial information about the cosmic forces at work, offering clues to one of the greatest mysteries of modern science. In addition to their significance for understanding dark matter and dark energy, superclusters provide us with valuable insights into the history and evolution of the universe. By studying the light emitted by galaxies at varying distances from Earth, astronomers can glimpse the state of the cosmos at different points in time. This historical perspective allows us to trace the universe's development from the rapid expansion immediately following the Big Bang to the formation of the first galaxies and stars. With each newly discovered supercluster, we gain another piece of the cosmic puzzle, enhancing our understanding of how large-scale structures like galaxies and superclusters have evolved and interacted throughout the universe's history. Moreover, the study of superclusters raises important questions about the ultimate fate of the universe. The way these massive structures are distributed and their movements may provide key insights into whether the universe will continue expanding forever, slow down, or eventually collapse in on itself. As scientists continue to observe and analyze these colossal formations, they bring us closer to understanding the long-term destiny of the cosmos. Every supercluster we examine offers a deeper appreciation of the vastness and complexity of the universe, reminding us of how much there is still to learn about the cosmos in which we live. The cosmic microwave background, CMB radiation, plays a central role in our comprehension of the universe's early origins. This faint, ubiquitous glow of radiation permeates the universe, offering a snapshot of the cosmos when it was just 380,000 years old. At this point, the universe had cooled enough for atoms to form, allowing light to travel freely for the first time. Prior to this era, the universe existed in an extremely hot and dense state, filled with particles and energy, and the CMB represents the remnants of that early phase. When astronomers observe the CMB, they are essentially peering back in time, studying the state of the universe when it was in its infancy. While the radiation is remarkably uniform, it contains minuscule fluctuations that reveal important information about the distribution of matter and energy shortly after the Big Bang. These fluctuations are crucial as they eventually led to the formation of galaxies and large-scale structures. By meticulously analyzing the patterns in the CMB's temperature variations, scientists can infer key details about the universe's density, composition, and the rate at which it has expanded over time. The CMB also supports the Big Bang theory, which posits that the universe began as an incredibly hot, dense point and has been expanding ever since. The uniformity of the CMB suggests that the early universe was in thermal equilibrium, while the slight variations in temperature confirm the predictions of cosmic inflation, a rapid expansion of the universe just moments after the Big Bang. These fluctuations set the stage for the universe's later development, allowing for the formation of galaxies and clusters despite the overall homogeneity observed on the largest scales. Far more than just a remnant of the universe's birth, the CMB serves as a cosmic time capsule, offering insights into the fundamental properties and conditions of the early universe. While the CMB offers valuable clues about the origins of the universe, cosmic rays provide a glimpse into its most energetic and violent phenomena. Cosmic rays are high-energy particles that travel through space at nearly the speed of light. When they collide with atoms in Earth's atmosphere, they produce showers of secondary particles that can be detected by scientists. By studying these cosmic rays, researchers can learn about the extreme processes occurring in distant astrophysical events, such as supernova, black holes, and neutron stars. A central aspect of cosmic ray research is determining their origin. Many cosmic rays are believed to originate from the remnants of catastrophic events like supernovae, where the immense energy released during the explosion accelerates particles to incredibly high speeds. By tracing the path of these particles back to their source, scientists can uncover the conditions in space that give rise to such powerful explosions. Additionally, cosmic rays act as messengers, revealing information about the magnetic fields and interstellar medium they pass through on their journey across the galaxy. These interactions can offer insights into the magnetic structures that influence star formation and the behavior of galaxies. Cosmic rays also have the potential to challenge and expand our understanding of fundamental physics. Some of the highest energy cosmic rays may provide evidence of new particles or forces beyond our current understanding. By capturing and studying these extreme particles, scientists hope to unlock new insights into the very nature of matter and energy, testing the boundaries of our physical theories. In this way, cosmic rays serve as both a window into the universe's most energetic phenomena and a tool for probing the fundamental laws that govern all matter and energy. The Oort cloud, a vast and mysterious region at the outermost reaches of our solar system, holds a unique and critical place in the study of our cosmic neighborhood. This spherical shell of icy bodies and potential comet-like objects extends up to 100,000 astronomical units from the Sun, almost halfway to the nearest star. The Oort cloud's vast expanse makes it an intriguing target for astronomers seeking to understand the origins and evolution of our solar system. One of the most captivating aspects of the Oort cloud is its role as a reservoir for long-period comets, which can take thousands or even millions of years to orbit the Sun. When gravitational forces from nearby stars or the tidal pull of the Milky Way stir objects in the Oort cloud, they are often sent on spectacular journeys toward the Sun. As these comets approach our star, they heat up, vaporizing and creating brilliant tails that light up the night sky. These dramatic displays offer a glimpse into the early materials that helped form our solar system, shedding light on the primordial building blocks of our cosmic neighborhood. In studying the Oort cloud, scientists are not only exploring the farthest reaches of our solar system, but also unlocking the secrets of the early solar nebula, the cloud of gas and dust from which the Sun and planets formed. By analyzing the comets and other objects that emerge from the Oort cloud, we can learn more about the conditions that existed in the early solar system and how the forces of gravity and time shaped the objects we observe today. The Oort cloud remains a critical area of interest for astronomers as they continue to piece together the story of our solar system's formation and evolution. The Oort cloud, a mysterious and distant region that marks the outermost reaches of our solar system, is widely believed to be a potential source of interstellar objects, those rare visitors that originate far beyond our cosmic neighborhood. These interstellar wanderers, such as the famous object Oumuamua, discovered in 2017, have captured the attention of astronomers, leading them to focus more closely on the Oort cloud as a potential nursery for such strange, far-traveling visitors. The recent discovery of Oumuamua, a cigar-shaped object that passed through our solar system, has revolutionized the way scientists think about the origins of such objects. It is speculated that the Oort cloud, a region populated by icy bodies far from the sun, could be a critical contributor to the influx of interstellar material. These interstellar travelers provide scientists with an unparalleled glimpse into the conditions, compositions, and evolutionary processes occurring in distant star systems, far beyond the boundaries of our own. By studying these foreign objects, we are not only enhancing our understanding of planetary formation, but also gaining insight into the diversity of worlds and the complex dynamics that shape them. Each comet or interstellar object carries with it a unique history, a tale of its formation, its journey across the galaxy, and its encounter with our solar system. These objects are more than just cosmic debris. They are messengers, providing clues about the early solar system and the conditions that prevailed in distant stellar environments. As astronomers continue to study the Oort cloud and its distant inhabitants, they uncover new secrets that challenge our fundamental understanding of space and time, expanding the boundaries of what we know about the universe. Looking deeper into the universe, the extreme environments of planets like Venus and Mars push the limits of our understanding about what makes a planet potentially habitable. At first glance, these planets seem to offer stark contrasts to Earth. Venus, often referred to as Earth's sister planet, is known for its thick, toxic atmosphere and surface temperatures hot enough to melt lead. The pressure on Venus's surface is over 90 times that of Earth, comparable to the crushing weight of being a mile underwater. These extreme conditions have led scientists to reconsider what makes a planet habitable, expanding the search for life beyond Earth's temperate environments. Could life exist in the upper atmosphere of Venus, where conditions are less extreme? In recent years, the discovery of phosphine, a potential biomarker, has sparked debates about the possibility of microbial life in Venus's clouds. While the planet's surface is inhospitable, these higher altitudes might offer a more Earth-like environment where life could persist. This has opened up new lines of inquiry into how life might adapt to extreme conditions and whether the traditional definition of habitability needs to be expanded. Mars, on the other hand, presents a different set of challenges. Once considered a potential haven for life, Mars is now recognized as a cold, dry world with a thin atmosphere that offers little protection from radiation. However, despite its harsh surface conditions, scientists have found compelling evidence suggesting that Mars may have once harbored life. The discovery of water, both in the form of ice at the poles and potentially briny liquid water under the surface, hints at the possibility that life could have existed in the past or may even persist in underground environments today. The rugged Martian landscape with its seasonal changes emphasizes the resilience of life and the importance of exploring even the most challenging environments to uncover the secrets of our cosmic neighbors. The study of Venus and Mars forces us to broaden our understanding of what makes a planet suitable for life. It encourages us to look beyond Earth-like conditions and to reconsider the adaptability of life in extreme environments. As scientists continue to investigate these worlds, they are challenged to think differently about the potential for life elsewhere in the universe, inspiring new theories and ongoing investigations into the limits of habitability. The discovery of ocean worlds within our own solar system has added another exciting dimension to the search for extraterrestrial life. Moons such as Europa, Enceladus, and Ganymede, orbiting the gas giants Jupiter and Saturn, are thought to harbor vast oceans beneath their icy surfaces. These moons present environments that could potentially support life, either as we know it or in forms entirely foreign to our understanding. Europa, one of Jupiter's largest moons, has fascinated scientists with its smooth, ice-covered surface that conceals a vast liquid ocean beneath. This ocean is believed to be in contact with Europa's rocky mantle, creating the potential for chemical reactions that could be conducive to life. NASA's upcoming Europa Clipper mission will aim to explore the moon's subsurface by studying its ice shell and conducting detailed reconnaissance to assess its potential habitability. The possibility of chemical nutrients and energy sources in this hidden ocean has sparked excitement among researchers, suggesting that life could exist in an environment very different from Earth's surface. Enceladus, a moon of Saturn, has also surprised scientists with its geysers, which shoot plumes of water vapor and ice particles into space. These geysers point to the presence of an active subsurface ocean, much like that of Europa. The Cassini mission revealed that these plumes contain organic molecules, key building blocks of life. This discovery suggests that Enceladus may have the necessary conditions for microbial life to thrive in its hidden ocean, making it a prime candidate in the search for extraterrestrial life within our solar system. Then there's Ganymede, the largest moon in the solar system, which also harbors a subsurface ocean. This ocean is believed to contain several times the volume of all of Earth's oceans combined, making it a significant potential habitat for life. The ocean of Ganymede could host a variety of chemical processes influenced by the moon's magnetic field and interactions with Jupiter's intense radiation. As missions and technology advance, the study of these ocean worlds continues to excite scientists, opening up new possibilities in the search for life beyond Earth. As our understanding of these moons and their oceans expands, the quest to uncover extraterrestrial life in our solar system remains one of the most intriguing endeavors in modern science. Whether life exists in these hidden waters or in other distant realms of the universe, each discovery brings us closer to answering one of humanity's oldest questions: are we alone? The study of exoplanet atmospheres has become another key area of exploration, offering a window into the complex chemistry of distant worlds. As astronomers observe exoplanets, they analyze the light that filters through an atmosphere during the planet's transit in front of its host star. This light reveals a unique spectrum of gases, offering clues not only about the composition of these far-off worlds, but also about the chemical processes occurring within them. By identifying gases such as carbon dioxide, methane, and water vapor, scientists can infer the types of chemical reactions happening on these exoplanets. For example, the presence of methane might suggest active geological processes or even biological activity, just as methane is produced by living organisms on Earth. This ability to detect and analyze the atmosphere of exoplanets allows astronomers to assess their habitability, providing further insight into the potential for life beyond our solar system. Each new discovery adds a layer to our understanding of how planets evolve, how their environments shape their chemical makeup, and how life may or may not emerge in such environments. As technology advances and our exploration capabilities expand, the search for habitable worlds continues to captivate the imagination of scientists and the public alike. Through the study of exoplanets, we are uncovering the intricate processes that govern planetary chemistry and how they might lead to the formation of life in diverse and unexpected ways. This ongoing journey into the cosmos invites us to expand our vision and to consider the many possibilities that await us in the uncharted reaches of space. The atmospheric conditions of exoplanets can vary dramatically, influencing everything from chemical reactions to the potential for sustaining life. When an exoplanet orbits close to its star, it is exposed to intense heat, leading to rapid chemical interactions that might not occur in cooler environments. On the other hand, planets farther from their stars, where the temperatures are lower, may host slower, more complex chemical reactions, potentially creating a completely different set of conditions conducive to life. By comparing the atmospheres of these distant worlds with those of planets in our own solar system, scientists can gain a deeper understanding of the vast spectrum of atmospheric compositions and behaviors that might exist across the universe. This comparative research not only enriches our understanding of specific exoplanets, but also offers valuable insights into the broader principles of atmospheric chemistry that govern planetary environments. As we continue to study the atmospheres of exoplanets, we are likely to uncover even more mysteries, and which could potentially lead us to discover worlds that harbor life, either in forms familiar to us or entirely alien, beyond anything we've yet imagined. The search for life-supporting conditions is thus far from being limited to Earth-like planets alone. the diverse range of atmospheres throughout the universe could open the door to entirely new forms of life and new definitions of habitability. Turning our attention to the gas giants within our own solar system, Jupiter, Saturn, Uranus, and Neptune, we find vital clues that help scientists decode the mysteries of planetary formation. These planets are not just massive, they represent fundamental elements in understanding how planets come into existence. Take Jupiter, for example. It is so enormous that its mass exceeds that of all the other planets in the solar system combined, by a significant margin. This colossal size results in an extremely strong gravitational field, one that likely played a crucial role in attracting and retaining vast amounts of gas during the planet's formation. Understanding the mechanisms behind how these gas giants accumulated such immense quantities of material is pivotal to developing accurate models of planetary origins. Another key feature of gas giants is their composition, primarily made up of hydrogen and helium, two of the most abundant elements in the early solar system. These giants provide a window into the conditions present during the formation of the solar nebula, the cloud of gas and dust that surrounded the young sun. Their makeup suggests that the early solar system had an abundance of the building blocks needed for the rapid formation of large planets, potentially explaining how these massive worlds could form so quickly in comparison to smaller rocky planets like Earth. The gas giants also offer valuable insights into the formation of planetary systems beyond our own. Their moons and rings, particularly those surrounding Saturn, provide a rich history of cosmic processes, collisions, accretion, and gravitational interactions. Saturn's iconic rings are not just a beautiful feature, they represent the remnants of a dynamic history, a past marked by the creation and destruction of moons. Some of Saturn's moons likely formed from the debris left over from the planet's early years, while others may have been captured from different parts of the solar system. This interplay between creation and destruction within a planetary system emphasizes the complexity of planetary development, offering a more comprehensive view of the forces at work in other star systems. Additionally, the location of gas giants in our solar system holds profound significance. These massive planets are located in the outer regions of the system, far from the sun's heat. This placement suggests that gas giants likely formed in a cooler environment, where gases could condense and accumulate into massive planets. The contrast between the outer gas giants and the inner terrestrial planets helps scientists understand how the distance from a central star can shape the formation and evolution of planetary systems. As we continue to study these giants, we can refine our models of planetary formation, offering new perspectives on how Earth-like planets might emerge in distant star systems. The moons of these gas giants also offer fascinating glimpses into the geological activity of celestial bodies, particularly in the case of Europa and Enceladus. These two moons, orbiting Jupiter and Saturn respectively, are some of the most exciting targets in our search for extraterrestrial life. Their surfaces exhibit signs of significant geological activity driven by tidal forces from their parent planets. These forces cause each moon to experience varying degrees of stress, which in turn generates heat within their interiors, a phenomenon known as tidal heating. For Europa, this tidal heating creates a subsurface ocean beneath its icy crust, where liquid water remains in a stable, life-sustaining state. The heat and pressure from Jupiter's gravitational pull are so intense that they cause geological features on Europa's surface, including cracks and ridges, suggesting that the ocean beneath is in constant interaction with the moon's rocky mantle. This provides scientists with tantalizing clues about the potential for life in the moon's deep ocean. Enceladus, too, offers compelling evidence of the geological forces at play beneath its icy surface. The moon's geysers, which erupt from its southern pole, shoot plumes of water vapor and ice particles into space, hinting at the presence of an extensive liquid water reservoir beneath its frozen exterior. These plumes suggest that Enceladus could be harboring a liquid ocean that may, just like Europa's, offer the necessary conditions for life. The dynamic nature of these moons, driven by tidal forces, makes them prime candidates for future astrobiological missions, which will further our understanding of the delicate interplay between gravitational forces and geological activity in the search for life beyond Earth. In our broader search for habitable worlds, red dwarf stars, also known as M-dwarfs, represent another intriguing avenue of exploration. These stars are the most common type in our galaxy, accounting for about 75% of all stars. They are smaller, cooler, and less luminous than our sun, yet their long lifespans make them particularly interesting when considering the potential for life on planets orbiting them. Red dwarfs burn for trillions of years, far exceeding the current age of our universe, offering a stable and enduring environment for any planets that orbit them. This longevity provides planets in the habitable zone, the region where conditions are just right for liquid water to exist, the opportunity to develop and sustain life for an astonishingly long time. Given their prevalence and stability, red dwarfs represent a key focus for astronomers and astrobiologists alike. Planets within the habitable zone of these stars might have the time they need for complex life to evolve, potentially making them prime targets in the search for life beyond our solar system. As we continue to explore these stars and their planets, we may uncover entirely new possibilities for the existence of life in the universe. The fascinating study of red dwarf stars has radically shifted our understanding of potential life beyond Earth. Red dwarfs, the most abundant stars in our galaxy, are far less luminous than stars like our Sun. This lower luminosity significantly impacts how we define habitable zones, the regions around a star where liquid water could exist on a planet's surface, a crucial ingredient for life as we know it. As these stars emit less light, the habitable zones must be much closer to the star compared to our solar system. However, despite the promise that red dwarfs hold, life around these stars presents certain challenges. Red dwarfs are notorious for their significant stellar activity, which includes frequent flares. These flares can release enormous amounts of radiation, capable of stripping away the atmospheres of nearby planets. Without an atmosphere to protect them, planets may struggle to sustain life. Yet, the planets that manage to retain their atmospheres may still offer a glimmer of hope for habitability. Those with strong magnetic fields, which could shield against stellar radiation, or those with natural processes that regenerate lost gases, might be more likely to support life. Recent discoveries have only heightened the excitement surrounding red dwarfs. Scientists have identified several Earth-sized planets within the habitable zones of these stars that could potentially harbor life. With more than 3 million red dwarf stars scattered across our galaxy, the potential for discovering worlds capable of sustaining life seems boundless. The long lifespans of red dwarfs, which can burn for tens to hundreds of billions of years, make them a focal point for astronomers for searching for life beyond our planet. The sheer number and longevity of these stars present an incredible opportunity to explore the universe's hidden corners. Meanwhile, the discovery of hot Jupiters, massive gas giants that orbit very close to their parent stars, has transformed our understanding of how planets form and migrate. These planets orbit at distances far closer to their stars than Mercury orbits the Sun. The discovery of hot Jupiters was unexpected, as traditional theories suggested that gas giants would form in the cooler outer regions of a solar system, far from their stars. Yet these massive planets challenge this classical view, raising questions about planetary migration. Initially, it was believed that hot Jupiters might have formed where we see them today. However, their very existence hints at a more dynamic and complex history. Researchers now believe that these giants likely formed further from their stars in the cooler regions and later migrated inward. This inward migration could have been triggered by interactions with other planets or the protoplanetary disk, a cloud of gas and dust surrounding a young star. Such migration could drastically alter the architecture of a planetary system, creating unique configurations that challenge our traditional notions of how planetary systems should behave. The study of hot Jupiters has prompted scientists to investigate various migration mechanisms. One widely accepted theory involves gravitational interactions that cause these massive planets to lose energy and spiral toward their stars. These interactions might occur through the exchange of momentum with smaller planets or the protoplanetary disk itself. Such migrations suggest that early solar systems may have been far more chaotic, with planets shifting orbits and undergoing dramatic transformations. Understanding these migration patterns is crucial for rethinking how common or diverse planetary systems might be. If such migrations occurred frequently, we could expect to see a wide array of planetary systems, not just the stable and well-ordered systems like our own. This research continues to shed light on the fascinating variety of worlds that could exist beyond our solar system. In the rapidly advancing field of exoplanet research, several recent discoveries have piqued the curiosity of scientists and the general public alike. One of the most intriguing finds is the discovery of super-Earths, planets larger than Earth, but smaller than Neptune. These planets have added an exciting new category to the growing list of exoplanet types. While many of these super-Earths fit neatly into existing classifications, some recent examples have defied expectations. For instance, scientists have identified a super-Earth with an atmosphere rich in hydrogen, suggesting a formation process different from what we initially thought. Another captivating revelation is the discovery of hot Jupiters. These gas giants, which orbit extremely close to their stars, experience scorching temperatures and possess unusual atmospheric compositions. One particular hot Jupiter was found to be evaporating, with its atmosphere being stripped away by the intense heat. This phenomenon not only challenges our conventional understanding of planetary formation, but also raises the possibility that these planets may evolve into entirely different types of objects over time. Adding to the mystery of the cosmos are rogue planets, celestial bodies that drift through space without being tethered to any star. A recent discovery of a rogue planet with a mass twice that of Earth has puzzled researchers. This rogue planet likely formed within a solar system, but was ejected into the void due to gravitational interactions. The idea that such lost worlds might be more common than we thought raises fascinating questions about their evolution and whether they could support life. Moreover, the detection of sub-Neptune planets has further challenged our traditional planetary classifications. These planets, which fall between super-Earths and Neptune in size, exhibit diverse atmospheres that vary widely in composition. One recent example featured a sub-Neptune with water clouds, hinting that these planets might possess conditions conducive to life despite their atypical classification. Each new discovery expands our understanding of exoplanets and demonstrates that the universe is far more diverse than we previously imagined. The gravitational influences of various celestial bodies also play a significant role in our understanding of life's potential beyond Earth. Gravity impacts the physical structure and behavior of organisms, and its effects would vary depending on the size and composition of the planet. On planets with lower gravity, such as Mars, organisms might grow larger or taller because they experience less downward force. On larger bodies, like Jupiter, the intense gravitational pull could limit the size and shape of living organisms, as they would need to withstand crushing pressure. Additionally, gravity affects essential biological processes, such as the circulation of fluids within organisms. For instance, blood in animals or sap in plants relies on gravity to circulate efficiently. Alterations in gravitational force could disrupt these processes, affecting growth, reproduction, and overall biological functionality. On planets with significantly different gravity from Earth, organisms might evolve entirely unique adaptations to cope with these changes. The result would be a stunning diversity of life forms adapted to their unique environments. The exploration of these various worlds, each with its own unique characteristics and challenges, provides invaluable insight into the broader question of life beyond Earth. From red dwarfs to hot Jupiters, rogue planets to super-Earths, the universe presents a wide array of possibilities. As our understanding of planetary formation and migration continues to evolve, the search for life beyond our solar system grows ever more exciting. The potential for discovering alien life, or at least environments capable of supporting it, seems more tangible than ever before. Gravity is not just a force that we feel on Earth. It is a fundamental element in the grand cosmic scheme, shaping everything from the formation of planets to the stability of atmospheres, and even the potential for life itself. At its core, gravity determines the capacity of a planet to retain gases, thereby sustaining an atmosphere. This atmosphere is essential for the regulation of weather, climate, and most importantly, for maintaining liquid water, which is considered one of the key ingredients for life as we understand it. Without gravity, these basic conditions would not be possible. Take, for instance, the moon. With only 1/16 of Earth's gravity, it is far too weak to hold on to a substantial atmosphere. This makes the moon a poor candidate for supporting life, as it cannot maintain the protective layers of gases necessary for the stability of life-sustaining elements like liquid water. Gravity, however, is not just a static force. It is a dynamic one, shaping the potential for life across the vast diversity of celestial bodies. The varying gravitational fields across different planets, moons, and other celestial bodies fundamentally impact biological processes, the development of organisms, and the retention of atmospheres. In this sense, gravity is a silent architect of life, its invisible hand either nurturing or hindering the conditions necessary for existence. Each planet, moon, and star system offers a unique scenario, compelling scientists to explore further as they search for signs of life beyond our own planet. One of the most fascinating aspects of planetary systems is the role moons play in the stability and evolution of their host planets. For example, Earth's large moon plays a pivotal role in stabilizing our planet's axial tilt, which is crucial for maintaining a consistent climate. Without this stabilizing force, the planet would experience wild fluctuations in its tilt, leading to extreme shifts in climate and making the development of life as we know it nearly impossible. Moons, through their gravitational interactions with their host planets, can also induce tidal forces, which have far-reaching effects. On Earth, these tidal forces create the ebb and flow of the oceans, but their influence doesn't stop there. The gravitational pull of the moon also affects geological processes, contributing to the shaping of our coastlines and even influencing atmospheric dynamics over long periods of time. The same tidal principles apply to other moons in our solar system. Their gravitational influence may stimulate volcanic activity, spur geological changes, or contribute to the long-term evolution of their host planets. But moons do not only influence the planets they orbit, they also provide protection. A relatively large moon can act as a shield, drawing in potential threats like asteroids and comets away from the host planet. During the early days of our solar system, when collisions between celestial bodies were common, this protective role may have been critical for the survival of emerging life forms. The moon's gravitational pull could have helped deflect some of these dangers, offering Earth a safer environment in which life could evolve. In some cases, moons themselves become intriguing targets for exploration, offering possible havens for life. Moons like Europa, one of Jupiter's satellites, and Enceladus, a moon of Saturn, have been identified as having subsurface oceans beneath their icy crusts. These hidden water worlds may harbor the fundamental building blocks of life, or perhaps life itself. As our understanding of these moons grows, so too does the potential for finding life in the most unexpected of places. As we continue to probe deeper into our solar system and beyond, moons serve as more than mere companions to their host planets. They are active participants in the cosmic dance, shaping the fate of the worlds they orbit and influencing the conditions necessary for life to thrive. Their impact on the development of their planets, their protective role against cosmic threats, and their potential to harbor life all emphasize their importance in the broader narrative of our search for life beyond Earth. Beyond our own solar system, the vast expanse of galaxies presents another intriguing mystery. Galaxies, with their spiral, elliptical, and irregular shapes, are among the most recognizable structures in the universe. Each galaxy represents a unique cosmic fingerprint shaped by gravitational forces over billions of years. The stunning spiral galaxies, for instance, are easily recognizable by their pinwheel-like structure, with arms of stars, gas, and dust whirling around a dense central core. These spiral arms are the product of complex gravitational interactions, where clouds of gas and dust are drawn together and set into motion. This rotation causes the material to flatten into a disk, with new stars forming in the spiral arms, creating a bright, active region of star formation. In contrast, elliptical galaxies present a more serene and aged appearance. These galaxies, lacking the spiral arms of their counterparts, have a more rounded or elongated structure. Their formation is often linked to the merger of smaller galaxies, a process in which gas is expelled and star formation slows down. This results in a population of older stars that dominate the light emitted by the galaxy. The light from elliptical galaxies often appears more yellowish due to the aging stellar population that resides there. Unlike their spiral counterparts, these galaxies are often quieter and less active in terms of star formation, but they offer valuable insights into the late stages of galactic evolution. Then there are the irregular galaxies, which do not conform to the neat categories of spiral or elliptical. These galaxies tend to have chaotic and disorganized shapes, often resulting from gravitational interactions with larger galaxies. The star formation within these irregular galaxies can be explosive, with new stars popping up in random regions, creating a patchwork of bright, vibrant areas contrasted with darker, more dormant voids. Their chaotic nature makes them particularly fascinating to astronomers, like offering clues about how galaxies evolve and how gravitational forces shape their development over time. Ultimately, the differences in structure and formation between spiral, elliptical, and irregular galaxies offer a glimpse into the diverse and complex processes that govern the universe. Each galaxy tells a story of its own formation, shaped by a series of gravitational interactions, star births, and mergers. This diversity not only enriches our understanding of the cosmos, but also highlights the fundamental role gravity plays in shaping the universe as a whole. At the very heart of our Milky Way galaxy lies a truly enigmatic and powerful force, Sagittarius A Sta, a supermassive black hole. Weighing approximately 4 million times more than our Sun, Sagittarius A exerts a gravitational influence that stretches across vast distances. Its presence shapes the orbits of nearby stars and clouds of gas, pulling them into its gravitational well. Despite its immense mass, however, Sagittarius A Sta remains surprisingly elusive, with much about its formation and growth still shrouded in mystery. Astronomers believe that Sagittarius A Sta may have begun as a much smaller black hole, possibly formed from the collapse of a massive star. Over millions of years, it likely consumed surrounding gas and stars, gradually building its size to become the cosmic giant that it is today. Its gravitational influence is far-reaching, affecting not only the dynamics of our galaxy, but also providing a unique laboratory for studying the nature of supermassive black holes. The study of Sagittarius A continues to intrigue scientists, offering insights into the mysteries of black hole formation, growth, and their role in the broader context of galaxy evolution. In this way, gravity remains an ever-present force, weaving through the fabric of space and time, shaping the destiny of planets, moons, stars, galaxies, and the very possibility of life itself. Its role in the formation of celestial bodies and its influence on the development of life are inseparable. Each new discovery in the cosmos, from distant galaxies to the moons of our own solar system, brings us closer to understanding the profound impact gravity has on the universe and our place within it. The search for life beyond Earth continues to unfold, but at every step, we are reminded that gravity is the force that governs the conditions necessary for life, both on Earth and across the stars. The origins and behavior of black holes have long been a subject of intense fascination for astronomers, yet despite decades of research, many aspects of these cosmic entities remain mysterious, particularly when it comes to their early formation and the conditions that allowed structures like Sagittarius A to emerge. Sagittarius A, the supermassive black hole at the center of the Milky Way, has raised numerous questions, with one of the most intriguing being its surprisingly quiet nature. Unlike other supermassive black holes across the cosmos, which actively consume matter and expel powerful jets of radiation, Sagittarius A Sta seems to be in a phase of relative dormancy. This peculiar behavior has sparked an ongoing debate. What governs the feeding habits of these black holes? What are the underlying processes that dictate their activity levels? These questions continue to captivate scientists who seek to unravel the enigmatic nature of these massive gravitational beasts. Recent observations have shown that while other supermassive black holes are voraciously feeding, creating intense radiation and powerful jets, Sagittarius A Sta appears to be much quieter. This raises even more questions. What has caused this black hole to enter such a calm phase? And why does it behave so differently compared to its cosmic counterparts? Some researchers believe that the surrounding environment, with its dense concentrations of gas and dust, may play a crucial role in limiting the amount of matter that can fall into the black hole. Others propose that Sagittarius A*Star may have simply exhausted its nearby supply of fuel, and thus remains in a dormant phase, waiting for fresh matter to drift in. In addition to its quiet nature, the surrounding region around Sagittarius A adds another layer of intrigue. This zone is home to a dense cluster of stars, gas, and dust, with some stars skimming dangerously close to the black hole's event horizon. These stars find themselves in precarious orbits, drawn in by the immense gravitational pull of the black hole. The big question is, what happens to these stars? Do they get pulled into the black hole, their material consumed in a spectacular display of cosmic power? Or do they manage to escape, preserving their paths in the galaxy? Understanding the fate of these stars is critical for understanding the overall dynamics at play within the galaxy's center. The mysteries of Sagittarius A contribute to the growing complexity of black holes as a whole, making it an invaluable subject for research. The more astronomers learn, the clearer it becomes that the universe is full of wonder and uncertainty. While Sagittarius A may hold many secrets, its behavior could eventually help to reveal broader truths about supermassive black holes in general, offering profound insights into the forces that govern these mysterious objects. Further out in the cosmos, another captivating story unfolds. The Andromeda Galaxy, our nearest spiral galaxy neighbor, is hurtling toward the Milky Way, a collision that is set to occur in roughly 4 billion years. Unlike the destructive impacts we might imagine from collisions here on Earth, this galactic event, known as a galactic collision, is vastly different. The vast emptiness of space means that the stars in these two galaxies are so far apart that the likelihood of a direct collision between them is almost non-existent. However, as Andromeda draws nearer to the Milky Way, gravitational forces will begin to pull the two galaxies closer together, setting the stage for a spectacular cosmic dance. At first, the two galaxies will pass by each other, their stars and gas drawn into each other's gravitational embrace. This gravitational interaction, often described as a cosmic tug-of-war, will cause the gas within the galaxies to compress, which could lead to the formation of new stars. The sheer forces at play will create dramatic changes in the galactic structures, ultimately leading to a merger that will unfold over the course of several billion years. This long-term process will see the two galaxies exchanging resources, merging their stellar populations, and forming a new, more massive galaxy. The resulting galaxy, sometimes referred to as Mila, will be a blend of the Milky Way and Andromeda, a new entity that will reflect the union of the two parent galaxies. The merger will significantly alter the shape and structure of both galaxies, giving rise to new patterns of stars, nebulae, and potentially even new black holes. Though this event lies far in the future, the study of Andromeda's approach offers a fascinating glimpse into the dynamic, ever-changing nature of the universe. Galactic mergers like this one are not rare in the cosmos. They play a vital role in the evolution of galaxies. And observing such an event can teach us much about both our past and our future. As Andromeda's gravitational pull brings it closer to the Milky Way, we are reminded of the interconnectedness of galaxies across the vast expanse of space. This cosmic journey is a powerful reminder that change is a constant feature of the universe, reshaping not only galaxies, but the very fabric of existence itself. This collision may be billions of years away, but it emphasizes the inherent dynamism of the cosmos and offers astronomers a unique opportunity to understand how galaxies evolve, collide, and form new structures. Even further in our quest for knowledge, we explore the cosmic web, an enormous structure that connects galaxies across the universe. This tapestry is woven together by dark matter, which acts as a kind of cosmic glue, holding galaxies together and guiding the formation of larger structures. At the heart of the cosmic web are the vast filaments of gas that stretch across space, connecting galaxies and forming the scaffolding for their growth. By studying these filaments, astronomers can trace the origins of galaxies and better understand how they've evolved over billions of years. One of the most captivating insights gained from studying the cosmic web is the role of gravity in galaxy formation. Dark matter filaments serve as the framework around which regular matter clusters, creating the dense regions where galaxies eventually form. By examining how these filaments distribute matter, scientists can uncover the history of galactic growth, revealing how galaxies interact with one another and shape the cosmic landscape. This interconnectedness highlights that the universe is not just a collection of isolated systems, but a vast network of relationships that are constantly evolving and reshaping. Moreover, the study of the cosmic web provides valuable clues about the early universe, particularly in the aftermath of the Big Bang. The distribution of galaxies across space reveals patterns of density that can help us understand the initial conditions of the universe, offering a clearer picture of how the first structures, galaxies and stars, began to take shape. By piecing together these patterns, scientists are able to reconstruct the history of the cosmos, shedding light on its infancy and the processes that set the stage for the universe we observe today. The cosmic web also reminds us that galaxies are not static entities. They are dynamic and constantly interacting with one another. Through gravitational forces and collisions, galaxies continue to influence each other, sometimes triggering bursts of star formation or even merging into larger systems. By studying these interactions, astronomers gain deeper insight into the evolution of galaxies and the ongoing processes that shape the universe. It reinforces the understanding that galaxies are not solitary objects. Rather, they are part of a larger, interconnected structure that governs the universe's evolution. The importance of magnetic fields in the formation and evolution of galaxies cannot be understated. These fields, generated by the movement of charged particles within galaxies, have a subtle but profound influence on star formation. Magnetic fields regulate the collapse of gas clouds, providing resistance against the force of gravity and slowing the process of star formation. This regulation allows the gas to cool and dissipate energy, creating a more stable environment for new stars to form. In this way, magnetic fields play a crucial role in shaping the very structure of galaxies, guiding the birth of stars and influencing their long-term evolution. In the earlier stages of star formation, when gas clouds are dense and gravitational forces begin to collapse them, magnetic fields can prevent the gas from collapsing too quickly. By exerting pressure on the gas, these fields slow down the collapse, allowing the gas to cool and dissipate energy at a more gradual pace. This controlled environment ensures that the conditions are optimal for the formation of new stars, ultimately guiding the cosmic cycle of birth, life, and death for the stars that populate galaxies. Through these intricate processes, magnetic fields help shape the evolution of galaxies, influencing everything from the birth of stars to the growth of massive black holes. They are an essential part of the cosmic machinery, working behind the scenes to regulate the forces that drive the universe's evolution. As we continue to explore the mysteries of the cosmos, it becomes increasingly clear that the interplay between gravity, dark matter, and magnetic fields is essential to understanding the vast, interconnected web that makes up the universe. Magnetic fields, often overlooked in discussions about the cosmos, hold immense power when it comes to organizing the movement of gas within galaxies. These fields serve as invisible guides, steering the flow of material across vast expanses. As they interact with the surrounding gas clouds, they can enhance turbulence, creating regions of increased density where stars are more likely to form. This turbulence, far from being chaotic, plays a critical role in the life cycle of galaxies. It facilitates the mixing of materials, redistributes energy, and drives the creation of new stars across different parts of a galaxy. Without this process, star formation would be restricted to a narrow region, potentially limiting the diversity and complexity of the galaxy itself. Interestingly, magnetic fields vary greatly across different types of galaxies, not only in strength, but also in configuration. These variations have profound implications for the rate and nature of star formation. For example, in spiral galaxies with their distinct, well-defined arms, magnetic fields are often highly organized. They channel gas into specific regions, promoting the formation of new stars in these concentrated areas. In contrast, irregular galaxies, which lack such defined structures, tend to have more chaotic magnetic fields. These complex interactions between magnetic fields and gas clouds are a testament to the dynamic, ever-evolving nature of galaxies. They underscore the crucial role that these invisible forces play in shaping the structure and evolution of the universe. Lenticular galaxies, which occupy an intriguing middle ground between an elliptical galaxies, are another fascinating aspect of galactic evolution. Visually, lenticular galaxies resemble a polished lens with a bright central bulge and a flattened disk, but without the spiral arms that make spirals so recognizable. These galaxies often contain dust and gas, though not as abundantly as their spiral counterparts. Their star populations tend to be older, contributing to their distinct position in the cosmic hierarchy. In terms of structure, lenticular galaxies feature a prominent central bulge, surrounded by a disk, but without the defined spiral arms seen in typical spirals. This lack of visible structure suggests that lenticular galaxies may have exhausted their gas reserves, halting the formation of new stars and putting them on a unique evolutionary path. The origins of lenticular galaxies are still a subject of debate. One prominent theory suggests that they may evolve from spiral galaxies as they deplete their interstellar gas through continuous star formation. Over time, as gas becomes scarce, the rate of star formation decreases, leading to the transition into a lenticular form. Alternatively, lenticular galaxies may result from the merger of two smaller galaxies, an event that causes the stars to redistribute into a more spheroidal shape, resulting in a smoother, more uniform appearance. In either case, lenticular galaxies provide astronomers with valuable insights into the life cycle of galaxies, offering clues about how environmental factors like gas depletion or galaxy mergers can influence a galaxy's development over millions or even billions of years. Dark matter, that mysterious and invisible substance that makes up a significant portion of the universe's mass, plays a key role in the structure and behavior of galaxies. Unlike ordinary matter, which we can detect through the light it emits or reflects, dark matter cannot be observed directly. Its presence is instead inferred through its gravitational effects. Dark matter forms an invisible scaffolding throughout galaxies, exerting a profound influence on their dynamics. It doesn't just help hold galaxies together, it also affects their shape, rotation, and even the formation of new stars. Most of the dark matter in a galaxy is found in a vast halo that extends far beyond the visible edges of the stars, gas, and dust. This halo exerts a gravitational force that influences how the other matter in the galaxy behaves. If dark matter is concentrated in a particular region, it can lead to a more flattened, disk-like structure as seen in spiral galaxies. On the other hand, if dark matter is more evenly distributed, it may result in the irregular spheroidal shape characteristic of elliptical galaxies. Dark matter also plays a crucial role in the rotation of galaxies. Its mass in the outer regions of a galaxy helps to keep stars rotating around the galaxy's center at higher speeds than would be expected based on the visible matter alone. This discrepancy is one of the key pieces of evidence supporting the existence of dark matter. In essence, dark matter serves as the unseen hand that guides the formation and evolution of galaxies. As astronomers continue to study its behavior, they hope to uncover more about how dark matter influences not just the structure of galaxies, but the very origins of the universe itself. One of the most dramatic and awe-inspiring events in the life of a galaxy is a merger. When two galaxies collide, they do not simply pass through each other. Instead, they draw upon their gravitational forces, slowly merging and coalescing into a new, larger galaxy. This process can lead to dramatic changes in the structure and dynamics of the galaxies involved. For instance, the collision of gas and dust clouds from the two galaxies can compress these materials, sparking waves of new star formation. It's as if the very fabric of the galaxy is being rewoven, with old stars making way for new ones in an explosion of cosmic activity. These mergers can lead to a variety of outcomes depending on the size and composition of the galaxies involved. In some cases, the merger may result in the creation of a more massive elliptical galaxy. In others, it might lead to a complex, multi-armed spiral. The sheer scale and energy of these events make galaxy mergers one of the most fascinating phenomena in the universe, illustrating the ever-changing nature of the cosmos. Moreover, these mergers have the potential to fundamentally reshape the structure and dynamics of entire galaxies. As two galaxies collide, their previously distinct forms can become distorted, giving rise to a wide range of new and often unpredictable shapes. Some of these new formations evolve into elliptical galaxies, while others develop peculiar shapes that defy classification. The gravitational forces at play during these mergers mix the stars and gas of the colliding galaxies, leading to the formation of an entirely new and diverse stellar population. In other words, when two galaxies merge, they do not merely create new stars from the cosmic chaos, they also alter the very makeup of the existing stellar populations within each galaxy. Over time, these cosmic interactions can lead to the creation of significantly larger galaxies, which in turn influence the surrounding cosmic environment. As galaxies merge, they also have the potential to foster the growth of supermassive black holes at their centers, a phenomenon now recognized as a common feature in many of the galaxies we observe today. The immense energy released during these galactic collisions can cause vast amounts of gas and dust to be expelled into the intergalactic medium, disrupting the star formation rates not just within the merging galaxies, but also in their neighboring regions. As such, galaxy mergers become pivotal drivers of galactic evolution over billions of years. They illustrate a dynamic and constantly evolving universe in which galaxies are not fixed, isolated entities, but are rather engaged in a perpetual cycle of interaction, collision, and transformation. The process of galactic mergers highlights the complexity of cosmic evolution, unveiling the intricate web of interactions that have shaped the universe as we understand it. Each observed merger serves as a window into the distant past, revealing how galaxies undergo profound changes and contribute to the ever-evolving cosmic landscape. By studying these interactions, astronomers gain valuable insights into the forces that drive the universe's expansion and the mechanisms behind its continual transformation. Understanding the structure of our own galaxy is an essential piece in the puzzle of mapping the broader universe. The Milky Way, with its distinctive spiral arms and dense central core, acts as a critical reference point for astronomers seeking to unlock the secrets of galactic dynamics. Through careful study of our own galaxy, scientists gain vital knowledge about the diverse types of star systems, the distribution of gas and dust, and the general behavior of galaxies across the universe. The Milky Way is far from a simple collection of stars. It is a complex, dynamic system in which gravity governs the movement of celestial bodies. This gravitational interplay helps astronomers to develop theories about how galaxies form, evolve, and interact. For instance, the spiral arms of our galaxy represent active regions of star formation, offering a glimpse into the life cycles of stars that can be compared to similar structures found in galaxies across the cosmos. Mapping the Milky Way also allows scientists to establish a cosmic geography that stretches beyond the boundaries of our galaxy. By studying the distances between stars within our own galactic neighborhood, astronomers can apply similar methods to measure the distances to galaxies billions of light years away. Techniques such as parallax and the use of standard candles become indispensable tools in expanding our understanding of cosmic structures and their interrelationships. Furthermore, observing the interactions between the Milky Way and neighboring galaxies, such as the Andromeda Galaxy, provides valuable insights into the gravitational forces shaping the universe. These observations offer a detailed picture of a dynamic cosmos where galaxies are in constant motion, colliding and merging in an ongoing process that shapes the grand tapestry of the universe. By delving into the complexities of our galaxy, we open new doors to deeper cosmic truths, revealing a clearer map of the vast and ever-expanding universe. The discovery of rogue galaxies wandering independently through the vast cosmic expanse offers an intriguing look into the evolution of the universe. These galaxies, unbound to any specific galactic group or cluster, drift freely through the intergalactic medium, challenging our traditional understanding of gravitational relationships in the cosmos. Their existence raises important questions about how galaxies form and evolve over cosmic timescales. One significant implication of rogue galaxies is that they provide a unique window into the dynamics of galaxy formation. Traditionally, we view galaxies as entities that form and evolve within clusters, interacting with one another through gravitational forces. However, rogue galaxies suggest that some galaxies may be ejected from their original groups due to high-velocity collisions or other gravitational interactions. This new perspective deepens our understanding of the life cycle of galaxies and the vast energies involved in their formation and merging. Rogue galaxies could also hold critical clues to the mysterious substance that makes up much of the universe: dark matter. Although dark matter remains invisible, its presence is detectable through its gravitational effects. By studying rogue galaxies, astronomers may gain valuable data about the distribution of dark matter throughout the cosmos, including areas where its influence is more pronounced or less understood. Lastly, the existence of rogue galaxies serves as a reminder of the expansive and complex nature of the universe. These wandering galaxies underscore the vastness of space and the diverse pathways that galaxies can take over billions of years. Each rogue galaxy provides a fascinating glimpse into the many possible narratives of cosmic evolution, reminding us that the universe is far more intricate than it might appear at first glance. As we continue to uncover the mysteries of these isolated galaxies, we expand our understanding of the fundamental processes that shape the cosmos, unveiling the wonders that lie beyond our own Milky Way. The Big Bang Theory, one of the most widely accepted scientific models, offers a comprehensive explanation for a multitude of phenomena observed in the universe today. At its core, this theory proposes that around 13.8 billion years ago, the universe began as an incredibly hot and dense point. The Big Bang, often described as the initial explosion, marked the birth of both time and space, setting into motion the ongoing expansion of the universe that we observe today. One of the most compelling pieces of evidence supporting the Big Bang Theory is the presence of cosmic microwave background radiation. This faint, omnipresent glow is the residual heat from the moment of creation, offering a snapshot of the universe just 300,000 years after the Big Bang, when protons and electrons combined to form neutral hydrogen atoms. As the universe expanded, this radiation gradually cooled, providing us with invaluable information about the early state of the cosmos. In addition, the observable phenomenon of galaxies moving away from us further reinforces the Big Bang Theory. When astronomers observe distant galaxies, they find that their light is redshifted, a clear sign that they are receding from us at high speeds. This observation aligns with the theory's prediction that the universe is still expanding. The farther a galaxy is, the faster it appears to be moving away. This expansion of space continues to play a critical role in shaping our understanding of the universe's evolution. Finally, the abundance of light elements, such as hydrogen and helium, spread throughout the cosmos, provides additional support for the Big Bang Theory. During the first few minutes after the Big Bang, the extreme conditions of heat and pressure allowed for nuclear fusion, leading to the formation of the simplest elements. The specific ratios of these elements observed in the universe today can be traced back to these early moments, offering a tangible link to the universe's origins and reinforcing the validity of the Big Bang Theory. The universe, as we understand it, was born from the colossal explosion we call the Big Bang. This event, occurring around 13.8 billion years ago, set in motion the processes that would shape everything we observe today. The Big Bang Theory is not just a framework for understanding the birth of the universe, but also serves as a profound lens through which we can explore the cosmos and our place within it. It explains not only the phenomena we see today, but also deepens our understanding of the vast and often mysterious workings of the universe. At the heart of this theory lies the idea of inflation. The theory of cosmic inflation suggests that in the moments just after the Big Bang, the universe underwent an astonishingly rapid expansion. This expansion occurred in a fraction of a second, so fast that it dramatically increased the size of the universe. The implications of this phenomenon are far-reaching and provide crucial insights into the universe's early stages. One of the strongest pieces of evidence supporting the theory of inflation comes from the cosmic microwave background radiation, CMB. This faint, almost imperceptible glow is a remnant from the early universe, a trace of the conditions that prevailed nearly 14 billion years ago. The CMB carries vital information about the universe's infancy, providing us with a snapshot of its early moments. Through this radiation, we can discern the uniformity and slight fluctuations in temperature that are present throughout the cosmos today. These patterns, crucially, match predictions made by the inflationary model, lending significant weight to the theory. The CMB serves as a cosmic fingerprint, a direct link to the universe's birth, and provides a window into its evolution. Another piece of evidence supporting inflation comes from the large-scale structure of the universe. The distribution of galaxies and galaxy clusters across the cosmos closely aligns with what the inflationary model predicts. According to this theory, the rapid expansion of the early universe seeded it with tiny density variations. These slight fluctuations, minuscule in the beginning, later grew into the massive gravitational wells that we now recognize as galaxies, clusters, and superclusters. Over time, these early fluctuations were amplified by gravitational forces, creating the complex cosmic structures we observe today. Inflation also offers a natural explanation for the observed isotropy of the universe. This concept refers to the uniformity we observe in the universe. No matter where we look, the cosmos appears roughly the same in all directions. Without inflation, the early universe would have been too small and too hot for such uniformity to develop across vast distances. The inflationary model stretches out any initial irregularities to incomprehensible scales, smoothing out the universe in a way that perfectly matches the observations we make with our telescopes. One of the more speculative but intriguing predictions of inflation is the existence of gravitational waves. These waves, created by quantum fluctuations in space-time during inflation's rapid expansion, are thought to be imprinted onto the fabric of the cosmos. Though we have yet to directly detect these waves, ongoing advancements in gravitational wave astronomy may eventually confirm their existence. Should that happen, it would serve as yet another testament to the role inflation played in shaping the universe we see today. With these pieces of evidence, the theory of inflation presents a compelling narrative for the origins of our universe. It has propelled our understanding forward, offering a clearer picture of how the cosmos evolved from a singularity into the vast, complex structure we observe today. Yet, even as we peel back the layers of the universe's history, the multiverse theory beckons, challenging our very understanding of existence. Traditionally, cosmology has been grounded in the belief that our universe, the vast expanse of stars, galaxies, and cosmic phenomena, is the entirety of existence. This view, rooted in the idea of a singular universe governed by universal laws of physics, has shaped our understanding of everything from the Big Bang to the formation of cosmic structures. However, the multiverse theory suggests a radically different possibility. According to this theory, our universe may be just one of countless others, each with its own distinct physical properties and governing laws. Imagine an infinite number of universes, each existing like a bubble within an enormous cosmic foam. Some of these universes might resemble our own, while others could be vastly different in ways we cannot yet imagine. The multiverse theory draws heavily on various interpretations of quantum mechanics and the theory of cosmic inflation. It posits that every decision, every quantum event could spawn a new branch of reality, creating parallel universes that coexist alongside our own. This notion challenges our most fundamental ideas about the nature of reality, opening up a Pandora's box of philosophical questions about the limits of science and the very fabric of existence. If true, the multiverse would have profound implications for everything we know about the cosmos. A key aspect of the multiverse theory involves what is known as the fine-tuning problem. Many of the features of our universe appear perfectly calibrated for the existence of life, something that seems exceedingly unlikely if these conditions arose by chance alone. For example, the strength of gravity, the charge of the electron, and the properties of the electromagnetic force all seem to be finely tuned to allow the formation of stars, planets, and life itself. The multiverse theory provides a potential explanation for this apparent fine-tuning. If there are infinite universes, then it becomes far more likely that at least one would have the precise conditions necessary for life. Rather than viewing our universe's conditions as improbably unique, the multiverse theory places them in a broader context where all possible outcomes are realized. Despite its allure, the multiverse theory faces significant scrutiny. One of the primary criticisms is that it may be impossible to test or falsify the existence of these parallel universes. Some argue that the multiverse drifts into the realm of speculation, far removed from the rigorous standards of scientific inquiry. Without empirical evidence, the theory remains controversial, and many remain skeptical about its validity. Yet the very act of exploring such radical ideas is reshaping how we think about the universe, pushing the boundaries of cosmology and fueling deep philosophical debates about existence, reality, and the limits of scientific knowledge. As we continue to probe the mysteries of the cosmos, our understanding of the universe will evolve. The conversation surrounding the multiverse, its implications, and its challenges to traditional cosmology will only deepen, urging us to reconsider our place in the grand cosmic story. One of the most fascinating concepts in modern cosmology is the idea of the cosmic horizon. This refers to the maximum distance from which light has had time to reach us since the beginning of the universe. To understand this concept, imagine standing in the middle of a vast field, only able to see as far as your eyes can take you. Beyond your vision lies a portion of the field you cannot access, simply because light hasn't had time to travel that far. On a cosmic scale, this is exactly what the cosmic horizon represents. The cosmic horizon marks the boundary of the observable universe, the region of the cosmos we can study and explore. Beyond this horizon, there are parts of the universe that remain inaccessible to us, not because our technology is insufficient, but because the light from those regions has not yet had time to travel to us since the Big Bang. The universe has been expanding, and as time passes, light from more distant regions is gradually reaching us, but some parts will forever remain beyond our observational reach. This idea dramatically shapes our understanding of the universe's structure and evolution, highlighting that there are limits to our observations and theories based on data beyond the cosmic horizon. The concept of the cosmic horizon serves as a reminder that there is much about the universe we will never be able to observe or comprehend, shaping the boundaries of both our scientific exploration and our philosophical reflections on the vastness of existence. The cosmic horizon is a cornerstone in our understanding of the universe, playing an essential role in cosmological theories about the universe's fate. As the universe continues to expand, this horizon also moves outward. However, as the universe stretches into the far future, a significant shift could occur. The cosmic horizon could begin to shrink. If the universe's expansion continues indefinitely, we might eventually reach a point where large regions of space become completely unreachable, effectively isolating them from the rest of the cosmos. This isolation raises profound implications not only for our understanding of cosmic evolution, but also for the very nature of the universe itself. The idea of a shrinking cosmic horizon challenges us to reconsider our place in the universe. The universe, which once seemed boundless and interconnected, could become an increasingly fragmented and inaccessible expanse. This scenario fuels a deeper curiosity about the limits of human understanding and the potential for knowledge about the universe beyond what we can presently observe. As such, the concept of the cosmic horizon pushes scientists to confront fundamental questions about the nature of reality, the infinite, and the ultimate fate of everything within the universe. It compels us to consider whether there are aspects of existence beyond our perception, hidden within the vast stretches of space and time. Understanding the cosmic horizon deepens our insight into the universe's history. It invites us to challenge our assumptions about the universe's beginnings and its potential future, forcing us to reckon with ideas of time and space that extend far beyond the reach of our daily experiences. Beyond this, it asks us to reflect on the significance of our place within the broader context of cosmic history, making the universe seem both incredibly vast and yet intimately tied to our own existence. While the concept of the cosmic horizon grapples with the fate of the universe, the cyclic universe model provides an entirely different perspective on cosmic evolution. Unlike the Big Bang theory, which suggests a singular origin for the universe around 13.8 billion years ago, the cyclic model posits that the universe undergoes a never-ending sequence of expansions and contractions. In this model, the universe reaches a maximum size before contracting again, eventually collapsing into a singular state, only to repeat the process. Each cycle would be marked by a big bang, followed by a big crunch, creating a rhythm of creation and destruction that stretches infinitely forward in time. This cyclic perspective radically redefines our understanding of time. Rather than viewing the universe as having a single, definitive beginning, the cyclic model introduces the idea that cosmic history is an eternal recurrence. Each cycle would be different, evolving in ways that might challenge our understanding of the laws of physics, the fate of stars, and the destiny of galaxies. This model raises profound philosophical questions. What happens to the fundamental forces of nature when the universe collapses? Do the same laws of physics govern each cycle, or might they change with each new iteration? Ultimately, the cyclic model invites us to see the universe not as a singular miracle, but as an ongoing saga, a cosmic narrative that perpetually unfolds. Both the Big Bang Theory and the cyclic universe model offer compelling explanations of the universe's origins, but they diverge on fundamental principles regarding time, existence, and the structure of reality. The cyclic universe suggests an ongoing process of creation, while the Big Bang Theory adheres to a one-time event that shaped everything we see today. Together, these models represent two distinct approaches to understanding the universe's evolution, and each offers its own insights into the mysteries of our existence. In recent years, scientists have made groundbreaking advances in the study of galaxy formation, particularly through the use of sophisticated simulations that model the universe's evolution over vast timescales. These digital recreations allow researchers to simulate the conditions of the early universe, taking into account a wide range of factors such as gravitational forces, dark matter, and the interactions between gas and stars. The insights gained from these simulations have revolutionized our understanding of how galaxies form, cluster, and evolve over time. One of the most significant discoveries to emerge from these simulations is the vital role of dark matter in galaxy formation. Dark matter, though invisible, exerts a profound influence on the structure of the universe. It provides the scaffolding upon which regular matter can clump together, eventually forming galaxies. Without dark matter, our universe would look drastically different. Far fewer galaxies would exist, and the cosmos would be far less structured. These simulations have also shown that galaxy formation is not a uniform process. Some galaxies form rapidly in dense environments, while others evolve more slowly in isolation, producing a stunning diversity of galaxy shapes, sizes, and compositions. The variety in galaxy formation patterns reveals just how complex the universe is. From the elegant spirals of our own Milky Way to the irregular galaxies found in the distant reaches of space, the different ways galaxies evolve highlight the dynamic nature of the cosmos. Simulations also shed light on how star formation within galaxies is regulated. Star formation is not a constant process, but is influenced by many environmental factors, such as the density of gas and interactions with neighboring galaxies. As researchers refine these models, they continue to uncover more about how galaxies grow and evolve over time. One of the most exciting theoretical frameworks in cosmology today is string theory, which seeks to unify quantum mechanics and gravity. At its core, string theory proposes that the fundamental particles making up the universe, such as electrons and quarks, are not point-like objects, but tiny vibrating strings. The vibration of these strings determines the properties of the particles, including their mass and charge. This idea offers a novel way of understanding the fundamental building blocks of reality, much like how the vibrations of a musical instrument determine the sound it produces. String theory presents a promising approach to resolving one of the greatest challenges in physics, reconciling quantum mechanics with gravity. Quantum mechanics does an excellent job of describing forces like electromagnetism and the strong and weak nuclear forces, but it struggles to explain gravity, which is described by general relativity. Gravity operates on a much larger scale, affecting massive bodies like stars and planets. String theory aims to bridge this gap by suggesting that gravity itself is not a separate force, but an intrinsic property of the universe's fundamental structure, emerging from the dynamics of vibrating strings. A striking implication of string theory is that it requires additional dimensions beyond the familiar three of space and one of time. According to string theory, there could be as many as 10 or 11 total dimensions, with the extra dimensions compactified or curled up, so small that they are imperceptible to us. The geometry of these hidden dimensions could have a profound impact on how the fundamental forces of the universe behave, including how gravity interacts with the other forces. Although string theory is still highly theoretical and lacks experimental validation, it holds immense potential. By offering a framework that integrates gravity with quantum mechanics, it could serve as the foundation for a theory of everything, a single theory that explains all the forces and particles of the universe. As we continue to explore the intricacies of string theory, we may come to realize that the universe is far more complex and interconnected than we ever imagined. Simulations also play a pivotal role in understanding dark energy, the mysterious force responsible for the accelerated expansion of the universe. Advanced computer models allow scientists to simulate the effects of dark energy on the large-scale structure of the universe. These simulations help researchers explore how dark energy interacts with matter and influences the expansion of space over billions of years. By observing how galaxies form and cluster, under the influence of both gravity and dark energy, scientists can gain a deeper understanding of how these forces shape the cosmos. In essence, these simulations are a powerful tool for unraveling the mysteries of the universe. They allow researchers to explore different scenarios, helping to predict the behavior of galaxies, dark matter, and dark energy over vast timescales. As our computational models improve, we are poised to unlock even more secrets about the origins and ultimate fate of the universe, bringing us ever closer to understanding the forces that govern all of existence. As the simulations evolve, they provide a fascinating glimpse into the very nature of our universe's expansion. These computer models reveal how dark energy began to dominate the dynamics of cosmic expansion around 5 billion years ago, triggering the accelerated expansion we observe today. By simulating various cosmic scenarios, scientists can probe the mysteries of dark energy, tweaking its properties to explore how subtle changes could impact the evolution of the cosmos. This computational approach is vital, allowing researchers to test a wide range of theories about dark energy's behavior. For example, by adjusting parameters such as the strength and nature of dark energy, scientists can observe the effects these changes have on the trajectory of cosmic evolution. This process enables a direct comparison between simulated data and actual astronomical observations, fostering refined theories and a more nuanced understanding of the universe's accelerating expansion. Through these iterative simulations, scientists are not just exploring dark energy itself, but also gaining crucial insights into the broader fate of the universe. As simulations bridge the gap between theoretical physics and observational astronomy, they guide researchers in developing models capable of explaining the universe's most complex and sometimes counterintuitive phenomena. Each new iteration brings scientists closer to answering one of cosmology's most profound questions. Why is the universe expanding at an ever-accelerating rate? These virtual explorations continue to unravel the mysteries of the cosmos, leading to new discoveries about the forces that shape the universe. They also touch on broader concepts like entropy, a fundamental concept in thermodynamics that describes the degree of disorder or randomness within a system. In the context of cosmology, entropy plays a pivotal role in understanding both the universe's evolution and its eventual fate. As the universe expands, it tends to move toward a state of higher entropy. This process has significant implications for the future of the cosmos. One potential outcome is a scenario in which dark energy's dominance leads to the eventual isolation of galaxies. As the space between them widens, the universe will continue to become more homogeneous, with energy and matter becoming increasingly spread out. This relentless expansion not only creates vast stretches of emptiness, but also drives entropy to new heights. In this case, the ultimate fate of the universe could be what scientists call the heat death, where all energy is evenly distributed and no thermodynamic free energy remains available. In such a state, processes that increase entropy would cease entirely, signaling the end of all physical activity. Conversely, an entirely different theory suggests that the universe could eventually collapse in on itself in a scenario known as the Big Crunch. In this model, the forces of gravity would overwhelm the expansion, pulling matter and energy back toward a single point. As the universe contracts, entropy continues to play a crucial role. The immense heat and density of the collapsing universe would produce even greater disorder, potentially setting the stage for a new singularity, a point of infinite density from which the universe could be reborn. Regardless of the specific fate, whether the universe expands into an empty, cold future or collapses in on itself, the overarching trend toward increasing entropy remains a constant. Entropy's inevitable rise underscores a fundamental aspect of the universe's nature. Complexity tends to dissipate over time, giving way to greater simplicity. Beyond the heat death and Big Crunch models, other theories like the cyclic model propose that the universe experiences repeated cycles of expansion and contraction. In this view, entropy increases with each cycle, though some energy is lost to black holes. The cyclic theory suggests that after each contraction, the universe could reset itself, leading to a new phase of expansion. Yet, even in this scenario, the inexorable rise of entropy suggests that complexity in the universe will ultimately give way to a simpler, more uniform state. The concept of entropy serves as a crucial framework for understanding the long-term fate of the cosmos. It offers a lens through which to explore the universe's destiny, raising profound questions that continue to captivate scientists and laypeople alike. It invites us to consider how, over vast timescales, the universe will evolve and whether it will ultimately succumb to a state of ultimate simplicity. Another cornerstone of cosmological research is the theory of cosmic inflation, which seeks to explain the rapid and exponential expansion of the universe in the first moments after the Big Bang. This theory proposes that immediately following the birth of the universe, it expanded at an astonishing rate, far faster than the speed of light, within a fraction of a second. This inflationary period smoothed out any irregularities in the universe's structure, resulting in the homogeneous and isotropic cosmos we observe today. One of the key aspects of inflation is the role of quantum fluctuations. As the universe expanded, tiny variations in density caused by these fluctuations were stretched across space. These fluctuations are believed to have seeded the formation of the galaxies, clusters, and large-scale structures we see in the universe today. Cosmic inflation, therefore, not only explains the uniformity of the universe, but also provides a mechanism for the creation of the structures that continue to evolve and shape the cosmos. In addition to quantum fluctuations, another significant aspect of cosmic inflation is the role of scalar fields. These theoretical fields are thought to have driven inflation, dominating the early universe with their potential energy. The exact nature of these fields remains an open question in cosmology, and different models propose various types of scalar fields that could influence the rate and duration of inflation. Each model leads to different predictions about the ultimate shape and fate of the universe, making inflation a vibrant area of ongoing research. These diverse models continue to shape our understanding of the early universe, offering potential answers to some of the most fundamental questions in cosmology. From the seeds of galaxy formation to the ultimate fate of the universe, the study of cosmic inflation, dark energy, and entropy continues to illuminate the pathways that the cosmos may take, whether towards an ever-expanding future or an eventual collapse into singularity. Each new discovery not only refines our current models, but also brings us closer to understanding the true nature of the universe's existence and its inevitable end. Inflationary theory, a critical cornerstone in modern cosmology, holds profound connections to several other significant cosmic phenomena, including dark energy and the cosmic microwave background radiation. The observational data gathered from these fields continues to lend robust support to the inflationary model, offering invaluable insights into the universe's composition and its dynamic evolution. As researchers relentlessly explore and test these theoretical frameworks, the quest to understand cosmic inflation remains one of the most thrilling frontiers of contemporary cosmology. It beckons us to probe deeper into the enigmatic mysteries of our universe, uncovering layers of knowledge about its origins, growth, and intricate workings. Meanwhile, meteor showers, those mesmerizing celestial displays, are far more than just beautiful spectacles. They occur when Earth passes through the trails of debris left behind by comets or asteroids. As these celestial bodies orbit the Sun, they shed tiny particles ranging from grains of sand to larger rocks. When Earth crosses the path of a comet, these particles enter our atmosphere at incredibly high speeds, often between 10 to 70 meters per second. The friction generated by their rapid entry causes them to heat up, resulting in the brilliant streaks of light we observe as meteors. These meteor showers offer much more than a chance to marvel at the night sky. They provide essential opportunities for astronomers to delve into the composition of comets and asteroids. By studying the light emitted during meteor showers, scientists are able to gather crucial information about the materials that make up these distant, icy bodies. This research aids in our understanding not only of the origins and evolution of our own solar system, but also of the potential hazards posed by near-Earth objects. In addition, meteor showers allow astronomers to gain insights into Earth's own atmosphere. As meteors blaze through the sky, they interact with atmospheric gases, creating ionization patterns that can be studied. These interactions provide valuable data on atmospheric dynamics and the chemical processes taking place at high altitudes. In this way, meteor showers serve as a bridge between the cosmos and our planet, illuminating both celestial phenomena and terrestrial processes. With continued observation and study, these cosmic events will play an increasingly pivotal role in shaping our understanding of the universe. Each meteor shower invites us to dive deeper into the mysteries of our solar system, offering a tangible link between the Earth we inhabit and the vast cosmos that surrounds us. Gravitational lensing, a truly captivating phenomenon, occurs when the gravitational field of a massive object, such as a galaxy or a cluster of galaxies, bends the light from a more distant object. This bending distorts the light, creating multiple, often blurry images of the background object, which amplifies our view of it. For astronomers, gravitational lensing is not merely an optical curiosity. It has become a powerful tool for uncovering the deepest secrets of the universe. One of the most significant implications of gravitational lensing is its ability to reveal the presence of dark matter. Although we cannot see dark matter directly, its gravitational influence can be detected through the distortions in light caused by lensing. By studying these distortions, scientists can infer not only how much dark matter exists in the foreground galaxies or clusters, but also where it is located. This crucial information enhances our understanding of the distribution and role of dark matter in the cosmos. Gravitational lensing also acts as a cosmic magnifying glass, enabling astronomers to observe distant, faint objects that would otherwise be beyond detection with current technology. Through lensing, researchers can peer into the early universe, observing the light from galaxies that formed shortly after the Big Bang. This leap back in time allows astronomers to refine their understanding of galaxy formation and evolution over billions of years. Moreover, gravitational lensing provides valuable insights into the expansion and structure of the universe itself. By measuring how light from lensed objects is distorted, scientists can refine models of cosmic expansion and explore the nature of dark energy. Thus, gravitational lensing not only enhances our understanding of distant cosmic objects, but also plays a vital role in our broader quest to unravel the mysteries of the universe, providing us with new ways to probe the very fabric of reality. Solar flares, intense bursts of radiation from the sun's atmosphere, represent another key phenomenon with far-reaching implications. These eruptions occur most often during periods of heightened solar activity and release enormous amounts of energy in the form of light and heat. As this radiation travels through space at the speed of light, it reaches Earth in just over 8 minutes, where it can have significant effects on space weather. Solar flares can disrupt the ionosphere, the layer of Earth's atmosphere where many satellites operate, and their impact can be felt in the form of technological disruptions. One of the most notable effects of solar flares is their ability to trigger geomagnetic storms. When a solar flare is accompanied by a coronal mass ejection, CME, a massive burst of solar wind and magnetic fields, the charged particles from the sun collide with Earth's magnetic field. This interaction induces electrical currents that can overload power grids, potentially damaging electrical infrastructure. Such disruptions can affect power supplies on a large scale, sometimes impacting thousands or even millions of people. The study of solar flares and their associated effects on Earth's magnetosphere is crucial for understanding space weather and its potential impact on modern technology. As we continue to advance our ability to monitor and predict solar activity, we gain a clearer picture of how these powerful events can influence everything from communication systems to power grids. Solar flares remind us of the immense power exerted by our sun and the delicate balance of forces that govern the relationship between our planet and the cosmos. In an age where space exploration and technology are integral to daily life, understanding solar flares and their impact is more important than ever in safeguarding the technological infrastructure that connects our modern world. Through the study of these diverse cosmic phenomena, whether the mysteries of cosmic inflation, the beauty of meteor showers, the depth revealed by gravitational lensing, or the disruptive power of solar flares, humanity continues its relentless pursuit of knowledge. Each new discovery brings us closer to understanding the universe's grand design and our place within it, inspiring future generations to reach ever further into the unknown. Solar flares, despite their natural beauty, are not without their disruptive potential. These intense bursts of energy from the sun send shockwaves through space, capable of significantly affecting communication systems on Earth. The impact is most pronounced in the polar regions, where the solar flare's charged particles can severely disrupt radio signals, making reliable communication a challenge. Satellites are especially vulnerable, as the radiation exposure can damage their sensitive electronics, causing malfunctions or even a gradual degradation in performance. Misjudging the power of a solar flare can lead to costly consequences for technologies we rely on daily, such as GPS, satellite television, and even aviation systems. These systems, which depend on precise and uninterrupted communication, are not immune to the forces of the sun. However, amid these potential threats lies a hidden beauty. The same energized particles that wreak havoc on technological systems also contribute to one of the most spectacular phenomena on Earth, the auroras. Known as the northern and southern lights, these vibrant, shimmering displays are a direct result of solar activity. When solar particles collide with Earth's atmosphere, they excite gases, causing them to emit light in an array of colors. The auroras serve as a visual reminder of the dynamic relationship between our planet and the sun. A reminder that while the forces of space weather can disrupt and damage, they can also create awe-inspiring natural light shows. Understanding solar flares and their impacts not only deepens our knowledge of space weather, but also aids in safeguarding our technology and adapting our lifestyles to the whims of our ever-changing sun. In a similar way, the study of redshift offers a profound understanding of the universe and its vast, expanding nature. Redshift occurs when light emitted by an object stretches as it travels through space, shifting toward the red end of the spectrum. This phenomenon is tied to the Doppler effect, the same principle that causes the sound of an approaching train to shift pitch as it passes by. In astronomy, when light from distant stars or galaxies shifts toward the red, it signals that these objects are moving away from us. This is a fundamental observation that allows astronomers to measure the speed at which celestial objects are receding, providing insight into their distance from Earth. The concept of redshift is intrinsically tied to the expanding universe. As space itself stretches, distant galaxies appear to move away from us, and the farther they are, the faster they seem to recede. This correlation between the extent of redshift and the distance of objects helps astronomers map out the universe, offering a glimpse into its vast structure and evolution over time. Beyond simply measuring distances, redshift is also a key to understanding the rate of the universe's expansion, a crucial element in cosmological studies. The expansion rate is often referred to as the Hubble constant, a value that plays a pivotal role in shaping our models of the universe's future. Whether the universe will continue to expand indefinitely, slow its growth, or eventually contract is a question that hinges on our understanding of redshift and the forces driving this cosmic evolution. Intriguingly, Redshift is not the only phenomenon that sheds light on the motion of celestial bodies. Blue shift, the opposite of redshift, occurs when light from an object moves toward the blue end of the spectrum. This typically indicates that the object is approaching us rather than receding. By examining both redshift and blue shift across the universe, scientists can gain a more complete picture of the movements and interactions of celestial bodies. These observations reveal not only the vast distances between objects, but also the underlying forces that shape the cosmos. Comets, often dubbed the dirty snowballs of the solar system, provide another key to unlocking the mysteries of our cosmic past. These icy bodies, with their elongated orbits around the sun, offer scientists a unique glimpse into the early solar system. Many comets follow long, elliptical paths that can take hundreds or even thousands of years to complete a single revolution around our star. By tracking these comets and observing their periodicity, the regularity with which they return, astronomers can learn about the conditions present when these icy bodies were formed. Comets are ancient relics, remnants of the primordial gas and dust that once coalesced to form our solar system. Their compositions, which include water ice, carbon dioxide, methane, ammonia, and organic compounds, hold valuable clues about the chemical environment of the early solar system. This suggests that comets could have played a pivotal role in delivering water, and perhaps even the building blocks of life, onto Earth during its formative years. The study of cometary materials helps scientists reconstruct the conditions that existed during the solar system's infancy, offering insights into how the planets came to be. Tracking the periodicity of comets provides an invaluable window into the past, revealing not only the processes that shaped our solar system, but also the dynamic forces that govern the formation of celestial bodies. Each comet's return is a reminder of the intricate dance of creation and change that has unfolded over billions of years. By understanding these patterns, we deepen our appreciation for the forces that shape not just our own planet, but the entire cosmos. The Pleiades star cluster, often referred to as the Seven Sisters, is another remarkable feature in our universe. Located about 400 light-years away in the constellation Taurus, this cluster consists of roughly 100 stars, with the 7 brightest easily visible to the naked eye. What makes the Pleiades particularly fascinating is its youth. The stars within the cluster are estimated to be only around 100 million years old, a relatively short time in cosmic terms. This youthful age makes the Pleiades an invaluable laboratory for studying the life cycle of stars, as it provides a snapshot of a crucial phase in stellar evolution. The stars in the Pleiades were all formed from the same giant molecular cloud, meaning they share a common origin. This shared history allows astronomers to observe and understand the processes that lead to star formation. By studying how these stars evolve over time, scientists can gain insight into the different stages of a star's life, from its birth to its eventual death. Among the stars in the Pleiades, there is a fascinating diversity. Some are hot, massive blue stars, while others are smaller, cooler stars. This diversity is significant because it provides clues about the different pathways stars take during their evolution. Massive stars, for example, burn through their fuel quickly and end their lives in dramatic supernova explosions. Smaller stars, on the other hand, burn more slowly and can last for billions of years before eventually reaching old age. By studying this range of stellar types, astronomers can gain a deeper understanding of the relationship between a star's mass and its lifespan, knowledge that is essential to our understanding of astrophysics and the broader processes that govern the evolution of stars across the universe. The Pleiades cluster, often referred to as the Seven Sisters, offers an unparalleled opportunity for scientific study, largely due to its distinct, well-defined boundaries. This makes it a prime target for understanding the complex processes of stellar interactions and the evolution of star clusters. The gravitational binding of the Pleiades is just weak enough to allow its stars to gradually drift apart, which provides astronomers with a unique vantage point to study the late stages of a star cluster's life cycle. Through careful observation, researchers can analyze how individual stars evolve within this cluster, offering vital clues not only about stellar development, but also about the broader dynamics of star clusters across the cosmic timeline. This ongoing process allows astronomers to delve deeper into understanding how stars form, interact, and ultimately fade away over vast periods of time. The Pleiades stands as a cornerstone in our understanding of stellar evolution, playing a pivotal role in shaping our knowledge of how stars and their environments change across eons. Turning to another remarkable phenomenon, planetary nebulae are some of the most visually striking cosmic structures, and they hold key insights into the life cycle of stars. These nebulae are formed when medium-sized stars, like our Sun, reach the end of their lives. After depleting the nuclear fuel in their cores, they can no longer sustain the nuclear reactions that keep them stable. As a result, their cores contract while their outer layers expand, ultimately being ejected into space. This process results in the creation of a luminous shell of gas and dust, what we call a planetary nebula. What makes planetary nebulae particularly fascinating is the chemical composition of the material they expel. Over billions of years, elements such as carbon, nitrogen, oxygen, and even heavier elements accumulate in the star's core and outer layers. When the star sheds these layers, it releases these elements back into the interstellar medium. This material becomes the essential building blocks for future generations of stars, planets, and possibly even life. In essence, planetary nebulae serve as the universe's recycling mechanism, redistributing the stellar materials that will later go on to form new celestial bodies. The dispersal of these elements enriches the surrounding regions of space, effectively contributing to the ongoing formation of stars and planetary systems. This cycle of birth, death, and rebirth plays a crucial role in the continuous evolution of galaxies, driving the cosmic process forward. Studying planetary nebulae gives astronomers valuable insights into not just the life cycle of individual stars, but also the broader cosmic processes that shape the universe. These stellar remnants offer a glimpse into the forces that shape the fabric of space, helping scientists track the flow of materials across the cosmos and providing a deeper understanding of how galaxies evolve over time. Magnetars, one of the most extraordinary types of celestial objects in the universe, stand apart from other stars due to their intense magnetic fields. These stellar giants are a subclass of neutron stars, but what sets them apart is their magnetic strength, up to 1,000 trillion times stronger than Earth's. This immense magnetism dictates nearly every aspect of their behavior, leading to a range of fascinating and extreme phenomena. One of the most astonishing characteristics of magnetars is their ability to release bursts of energy, often in the form of X-rays and gamma rays. These bursts occur when the star's magnetic field suddenly changes, or when stored magnetic energy is released in a dramatic flare. In moments of high magnetic intensity, a magnetar can release more energy in a few seconds than the sun will emit over its entire 10 billion year lifetime. This makes magnetars not only incredibly fascinating to study, but also vital for advancing our understanding of the physics of extreme environments. While typical neutron stars are also born from supernova explosions and possess strong magnetic fields, their magnetism does not compare to the vast forces at work in magnetars. The unique characteristics of magnetars make them ideal candidates for studying both stellar evolution and the fundamental forces governing the universe. The extreme magnetism of these stars affects everything from the structure of the star itself to the behavior of nearby matter. The surrounding space, often deformed by the intense magnetic fields, becomes a laboratory for understanding the complex interactions of radiation, matter, and magnetism. The study of magnetars opens new avenues in astrophysics, allowing scientists to explore the boundaries of what we know about the universe's most extreme phenomena. Moving beyond individual stellar objects, the universe's vast and intricate structure is made more apparent by the existence of cosmic filaments. These filaments, composed of dark matter, gas, and galaxies, form an interconnected web across the cosmos, essentially acting as the skeleton of the universe. The study of these filaments provides crucial insights into the distribution of matter throughout the universe, shedding light on the processes that shape galaxies and galaxy clusters over vast stretches of time. The patterns formed by cosmic filaments reveal a universe that is far from uniform, with areas of higher density where filaments intersect. These intersections, known as cosmic nodes, serve as gravitational anchors, drawing in galaxies and other forms of matter. In these regions, new galaxies are more likely to form, while the gravitational pull of the filaments shapes the dynamics of the surrounding space. These cosmic threads also give us clues about the elusive dark matter, which forms the unseen scaffolding that holds the universe together. By studying the alignment and structure of these filaments, researchers are able to map out the distribution of dark matter, providing a deeper understanding of its role in the overall architecture of the universe. The study of cosmic filaments not only helps us understand the large-scale structure of the universe, but also offers key insights into the evolution of galaxies and the forces that govern the cosmos. Through these observations, we gain a clearer picture of the vast, interconnected web of matter and energy that forms the foundation of the universe itself. Studying cosmic filaments offers profound insight into the dynamic forces that shape our universe. These vast structures, often invisible to the naked eye, serve as cosmic threads weaving galaxies, clusters, and other celestial bodies together. As matter accumulates along these intricate threads, it creates a natural blueprint, revealing the powerful influence of gravity and other cosmic forces that have been at work for billions of years. By analyzing the evolution of these filaments, scientists are able to investigate the forces that drive the expansion of the universe and explore the enigmatic role of dark energy in this ongoing cosmic dance. Understanding how matter coalesces and evolves along these filaments opens a window into the far-reaching impacts of forces that are constantly at work, sculpting the very fabric of the cosmos. Observing these filaments is like mapping the grand architecture of the universe itself, providing an unprecedented opportunity to see the universe as more than just a random collection of stars and galaxies. Rather, it reveals a deeply organized and beautiful system shaped by fundamental forces that we are only beginning to comprehend. The more we study these cosmic structures, the clearer it becomes that our universe is far from chaotic. It is instead an intricately designed entity, influenced by forces that have been shaping it since its inception. The study of cosmic filaments enriches our understanding of the universe's evolution and helps us predict the future of cosmic structures, revealing not only how the universe formed, but how it will continue to evolve. In a similar vein, atypical stellar events, such as novas, provide captivating glimpses into the life cycles of stars, offering a front-row seat to the violent processes that govern their birth, evolution, and eventual death. A nova occurs when a white dwarf star, part of a binary system, pulls in gas and hydrogen from its companion star. Over time, this material builds up on the surface of the white dwarf, triggering a runaway nuclear reaction that causes a sudden and dramatic increase in brightness. The spectacular explosions that follow reveal critical stages of stellar evolution, providing scientists with vital information about the makeup and history of stars. The chemical signatures left behind by these explosive outbursts can reveal much about the composition of the stars that generated them. Through the light emitted by a nova, astronomers can detect the elements that are being ejected into space, shedding light on the materials present in the original stars and how they evolved over time. These chemical enrichments play a crucial role in spreading heavier elements throughout the universe, contributing to the formation of new stars, planets, and even life itself. Without these stellar explosions, many of the elements necessary for life would remain trapped in the cores of dead stars. Furthermore, the study of novas allows scientists to explore the intricate relationships between different types of stars within their environments. By analyzing the binary systems in which these events occur, researchers can observe the gravitational interactions between the stars and gain insights into their lifespans and evolution. This, in turn, enhances our ability to predict when similar events might occur across the universe, providing a deeper understanding of stellar life cycles beyond our solar system. Novas, in their breathtaking splendor, are more than just spectacular explosions. They are windows into the inner workings of the universe, revealing the delicate balance between creation and destruction that shapes the cosmos. In a broader sense, the study of atypical stellar phenomena like novas expands our appreciation for the universe's complexity. Each nova is a reminder that stars, though seemingly calm and stable, lead tumultuous and dynamic lives, undergoing dramatic transformations that ultimately influence the structure of the universe. Through these observations, we gain not only a deeper understanding of the stars themselves, but also a richer appreciation for the forces that drive cosmic evolution, shaping the universe as we know it. Turning to the Goldilocks zone, also known as the habitable zone, this region around a star offers a critical framework for understanding the potential for life beyond Earth. It is the area where conditions are just right for liquid water to exist on the surface of a planet, not too hot and not too cold. This concept is inspired by the fairy tale of Goldilocks, who seeks things that are neither too extreme but perfectly suited to her needs. Earth sits comfortably within this zone, allowing it to maintain the vital ingredient for life, liquid water. Water, as we know, is essential for life because it acts as a solvent, facilitating the complex chemical reactions necessary for the existence of life forms. While scientists entertain the possibility that life might exist in extreme environments, such as those found deep within the Earth's crust or in the frozen reaches of space, the search for extraterrestrial life typically begins with the identification of planets within the Goldilocks zone. This is because these planets are more likely to have stable conditions that could support the development of ecosystems similar to our own. When astronomers search for exoplanets, planets that orbit stars beyond our solar system, they pay particular attention to their distance from their respective stars. If a planet is too close to its star, the heat could cause water to evaporate, making life unsustainable. On the other hand, if a planet is too far from its star, any water present might freeze into ice. Finding a planet within this sweet spot greatly increases the chances that it could harbor liquid water, and therefore the conditions necessary for life. As we continue to explore the universe, the Goldilocks zone serves as an essential guideline for our search for extraterrestrial life. It helps us narrow down the vast expanse of potential planets and focus our efforts on those that are most likely to have habitable environments. This search is not just a scientific endeavor. It fuels our hopes and dreams of discovering life beyond Earth. It stirs the imagination, urging us to wonder whether we are truly alone in the cosmos or whether there are other forms of life waiting to be discovered. Similarly, the study of extremophiles, organisms that thrive in the most extreme environments on Earth, expands our understanding of life's resilience and adaptability. From deep-sea hydrothermal vents to the frozen Arctic tundra, these organisms can survive in conditions of extreme heat, acidity, pressure, and radiation. Their existence challenges the assumption that life requires Earth-like conditions and opens up new possibilities for what environments could support life elsewhere in the universe. By studying extremophiles, scientists uncover valuable insights into the biochemical pathways that enable life to endure in such hostile conditions. Take thermophiles, for example, which flourish in boiling hot springs. These organisms have evolved unique proteins that remain stable and functional even at extreme temperatures. Understanding these adaptations not only deepens our appreciation for life's tenacity, but also suggests that life might be more robust and adaptable than we once thought. This opens up exciting possibilities for life in extreme environments beyond Earth, such as on the boiling surface of Venus or the icy moons of Jupiter, like Europa. The study of extremophiles underscores a key idea. Life, in all its forms, is far more adaptable and resilient than we might have imagined. It suggests that just as life on Earth can thrive in the most extreme conditions, life could potentially exist in environments that we once thought were too harsh to support it. As we continue to explore the cosmos, the discovery of extremophiles serves as both a guide and an inspiration, challenging us to rethink our assumptions about the conditions necessary for life and pushing us to explore the farthest reaches of the universe in search of the extraordinary. Through the study of cosmic filaments, novas, the Goldilocks zone, and extremophiles, we are embarking on a journey that not only deepens our understanding of the universe, but also challenges our very perceptions of life, its origins, and its future. Each discovery adds a new layer to the grand narrative of the cosmos, one that is still unfolding and rich with mysteries yet to be unraveled. Extremophiles, the remarkable organisms capable of thriving in the most inhospitable environments on Earth, have captured the imagination of scientists and expanded our understanding of life's resilience. These organisms have spurred interest in the potential for life beyond our planet, particularly in extreme environments where survival was once thought to be impossible. The discovery that Mars, for example, harbors salty brines in certain regions has led scientists to wonder whether microbial life, similar to Earth's extremophiles, could exist there. This possibility is not confined to Mars alone. As the exploration of the solar system continues, the study of extremophiles on Earth has proven invaluable in guiding researchers to search for life in environments previously considered uninhabitable, including moons, asteroids, and distant planets. These resilient organisms offer not just a testament to the adaptability of life, but also a blueprint for scientists as they look for signs of life in the far reaches of space. The more we learn about extremophiles, the better prepared we are to recognize the potential for life in environments that challenge our current understanding of habitability. The quest to answer one of humanity's most profound questions, whether we are alone in the universe, may be closer than we think. Through extremophiles, we are increasingly able to imagine life thriving in places that were once deemed impossible. Yet, searching for life beyond Earth is far from straightforward. Detecting biosignatures, indicators of life on distant exoplanets, presents a multitude of challenges. For one, many of the planets we are interested in lie light years away, often in star systems that are so faint we cannot observe them in detail. The amount of light that these distant worlds reflect is often minimal, and their host stars typically outshine any faint signals that could suggest the presence of life. This overwhelming brightness makes it exceedingly difficult to identify the faint traces of a biosignature amidst the star's glare. Another obstacle is the interpretation of spectral data. When light from a star passes through a planet's atmosphere, certain wavelengths are absorbed or scattered by gases, creating a unique spectral fingerprint. This fingerprint can hint at the presence of certain molecules, but the challenge arises in the fact that many gases produced by biological processes also have non-biological counterparts. Take methane, for example. Both living organisms and geological processes can produce methane. Discerning whether a gas is a sign of life or a result of geological activity requires highly advanced analytical techniques and a deep understanding of the planet's environment. Technological limitations also play a significant role in the complexity of this search. Current telescopes, despite their impressive capabilities, still lack the sensitivity required to detect faint biosignatures on distant exoplanets. Although promising advancements in space telescopes are on the horizon, designed to observe exoplanets in greater detail with improved techniques, many of these projects are still in their conceptual stages or require substantial funding and development before they can become a reality. As we refine our instruments and push the boundaries of our capabilities, the task of capturing reliable biosignatures remains a long-term challenge. The inherent variability of life adds yet another layer of complexity to our search. Life on Earth has evolved in an astonishing array of environments, resulting in diverse biochemical processes. As a result, our assumptions about what constitutes a biosignature could be too narrow. Life elsewhere in the universe may utilize elements or produce gases that we have not yet considered, which could completely alter our approach to detecting biosignatures. The search, therefore, is not merely a technological challenge. It requires us to think more broadly and expansively about the forms life might take, opening up new avenues for discovery. At the heart of this quest is the mystery of life's origins. For centuries, scientists and philosophers have been captivated by the question of how life began on Earth. Numerous theories have been proposed, each offering a different perspective on the origins of life. One of the most well-known theories is the primordial soup hypothesis, which suggests that life emerged in a warm, nutrient-rich body of water. According to this theory, simple organic molecules formed under the right conditions, eventually leading to the creation of more complex structures. This idea gained momentum in the 1950s when researchers conducted experiments that replicated early Earth conditions and successfully created amino acids, the building blocks of proteins. Another prominent theory is the hydrothermal vent hypothesis, which proposes that life could have originated deep within Earth's oceans around hydrothermal vents. These vents, where superheated water rich in minerals rises from the Earth's crust, provide the right conditions for chemical reactions to occur. Such environments could have catalyzed the formation of early life forms. The unique chemistry of these extreme conditions offers compelling evidence that life could arise in places very different from what we typically consider habitable. As scientists delve deeper into understanding the origins of life on Earth, they are also expanding their search for life beyond our planet. This quest is guided by the field of astrobiology, which seeks to explore the potential for life and environments throughout the universe. By studying extreme environments on Earth, acidic lakes, frozen tundras, and the depths of the oceans, researchers are gaining insight into how life might survive on other celestial bodies. Moons like Europa, one of Jupiter's moons, and Enceladus, a moon of Saturn, are prime candidates for exploration due to their subsurface oceans, which may harbor the conditions necessary for life. The relationship between the theories of life's origins and the search for extraterrestrial life is profound. The more we understand about how life began here, the better equipped we become to identify signs of life elsewhere. By expanding our definition of where life can thrive, researchers are broadening their search to include not only planets but also moons. As a result, the universe begins to seem less isolated and more alive with possibilities. This search is ultimately a quest not just for alien life, but also for a deeper understanding of life itself and our place in the cosmos. The concept of panspermia adds another fascinating dimension to this search. This theory suggests that life, or at least the building blocks of life, might travel between planets and even between star systems. According to the panspermia hypothesis, microscopic life forms, such as bacteria or spores, could be ejected into space following powerful impacts on their home planet. Once in space, these resilient microorganisms could survive the harsh environment carried along on comets or meteorites and eventually land on other planets or moons. One of the intriguing aspects of panspermia is the idea of natural interplanetary exchange. According to this theory, Earth's life could have originated from microorganisms that traveled through space for millions of years before finally settling here. Conversely, life from Earth might have made its way to Mars or other celestial bodies. This idea opens up a wealth of possibilities about our cosmic history. What if life exists elsewhere? And it is not just a case of life beginning independently on each world, but rather a cosmic exchange. This notion takes us into the realm of speculative thought, raising profound questions about the nature of life and the potential for intentional seeding from extraterrestrial civilizations. Although there is no direct evidence to support this idea, the possibility invites us to imagine the far-reaching implications of life's cosmic journey. As we continue to push the boundaries of space exploration and technological advancement, our search for extraterrestrial life is becoming more exciting and complex. Extremophiles provide a powerful reminder that life can adapt in ways we may never have anticipated, and this adaptability might be key to discovering life on other worlds. The challenges are great, but so too are the possibilities. With each new discovery, we edge closer to answering one of humanity's most profound questions. Are we alone in the universe? Studies of extremophiles, organisms that thrive in the most extreme conditions on Earth, provide compelling support for the panspermia hypothesis, a theory suggesting that life, or at least the building blocks of life, could spread across the cosmos. These resilient organisms have evolved to withstand harsh conditions that would be lethal to most other forms of life. They endure intense radiation, high vacuum, and extreme temperatures, demonstrating that life could survive the perilous journey through the vacuum of space. As we continue to explore the implications of panspermia, our understanding of life's origins could be fundamentally reshaped, broadening our view of what is possible in the vast universe. A significant frontier in this exploration lies in the detection of biosignatures in the atmospheres of distant exoplanets. The search for evidence of life beyond our planet has moved into an exciting new phase, driven by the advanced tools of planetary science and astrobiology. Scientists use a technique known as spectroscopy to probe the atmospheres of exoplanets, analyzing the light that passes through or reflects off them. This light contains crucial information revealing the chemical makeup of a planet's atmosphere through its unique spectral fingerprint. The focus of much of this research is to identify gases that might signal biological activity. For example, a combination of oxygen, methane, and water vapor in a planet's atmosphere could suggest the presence of life. Under normal circumstances, these gases would react and neutralize each other. The simultaneous presence of all three, however, points toward a fascinating possibility. These gases might be replenished by living organisms or by some unknown geological processes that work in ways we don't yet fully understand. Astronomers typically rely on space-based telescopes to conduct this research, as Earth's atmosphere often obstructs our view of distant worlds. These telescopes capture the light from a star behind an exoplanet during a transit as the planet moves across the star's face. As the planet blocks a portion of the light, scientists can analyze the remaining light to glean crucial data about the planet's atmosphere. The light that filters through can reveal hidden clues about the planet's composition and its potential to support life. The James Webb Space Telescope, set to launch with even greater sensitivity and resolution, is expected to enhance our ability to probe distant worlds. With these advancements, scientists will be able to search for specific biosignatures with unprecedented clarity. This leap forward in technology could open the door to a new era in our understanding of exoplanets, enabling us to identify potentially habitable worlds beyond our solar system with a level of detail we have never had before. As we continue to investigate these far-off realms, the pursuit of knowledge drives us to ask, what if life does exist beyond Earth? The discovery of microbial life on Mars, for example, would be a monumental breakthrough, challenging everything we know about the conditions necessary for life. For decades, scientists have speculated about the potential for life on other planets and moons in our own solar system, particularly those with environments that differ drastically from Earth's. Finding even the simplest forms of microbial life would fundamentally change our understanding of how life can exist in extreme conditions, expanding our view of the essential ingredients needed for life. If microbial life were confirmed on Mars, it would suggest that the building blocks of life are not as rare as we once thought, and could be more common throughout the universe than we had imagined. This discovery would likely prompt a re-evaluation of other celestial bodies in our solar system, such as Europa, one of Jupiter's moons, and Titan, one of Saturn's moons, both of which harbor environments that, though vastly different from Earth's, may still support life. The presence of microbes on Mars would serve as a powerful signal that life can arise in a variety of settings, from warm and wet environments to cold, harsh landscapes. This realization would challenge our assumptions about where life can exist, suggesting that life could thrive in conditions we once considered inhospitable. Moreover, it would raise profound questions about evolutionary processes. If life developed independently on Mars, it would provide compelling evidence that life is not a unique phenomenon bound to Earth, but could arise in similar conditions elsewhere in the universe. Such a discovery would trigger a paradigm shift in how we view evolution, suggesting that once the necessary ingredients for life are present, life has a tendency to emerge. This shift would not only encourage deeper exploration into Mars and other moons in our solar system, but it would also fuel our search for life on distant exoplanets orbiting other stars. If microbial life can exist in the diverse environments within our solar system, why not on other planets beyond? The confirmation of microbial life on Mars would redefine the parameters of the search for life and intelligence in the cosmos. It would fundamentally alter our understanding of the universe, suggesting that life is not a rare anomaly but a universal phenomenon that could exist in many forms, just waiting to be discovered. Meanwhile, the discovery of organic compounds on celestial bodies such as comets and asteroids has profound implications for how we view the origins of life and the chemical diversity of the universe. Organic compounds, molecules that consist primarily of carbon, hydrogen, oxygen, nitrogen, and other elements, are the essential building blocks of life. The discovery of these compounds in space indicates that the ingredients necessary for life are not exclusive to Earth, but exist in various forms throughout our solar system and potentially beyond. One of the most intriguing implications of these findings is the theory of panspermia. According to this theory, life could have been distributed across the cosmos via comets, asteroids, and other celestial bodies, with organic compounds acting as the building blocks of life. If these compounds are found in environments where conditions are right for life, it raises the possibility that these compounds could be the precursors of life elsewhere in the universe, or that they may have contributed to the development of life on Earth itself during its early years. Imagine for a moment that our planet was seeded with the very essence of life, brought to us by ancient celestial wanderers. The idea that life may have originated not just here, but could have spread across space through the impact of comets and asteroids, offers a fascinating new perspective on the origins of life. It suggests that life could be more widespread in the universe than we ever thought possible, and that Earth itself may be just one chapter in a much larger story of cosmic life. As we continue to unravel these mysteries, we are left to ponder a crucial question. Are we truly alone in the universe, or is life in all its forms more common than we can imagine? The discoveries of extremophiles, microbial life on Mars, organic compounds in space, and the potential for panspermia are all part of a growing body of evidence suggesting that life might not be a rare, earthbound phenomenon, but a universal force ready to emerge wherever the conditions are right. The discoveries made in the field of space science continue to push the boundaries of our understanding, particularly in the search for extraterrestrial life. As scientists delve deeper into the specific types of organic molecules found across the cosmos, they are uncovering vital clues about the chemical processes that take place in the farthest reaches of space. Each comet, asteroid, and celestial body that we study offers us a unique snapshot of the early solar system, a time when Earth itself was still forming. These stories, carried by the remnants of ancient space bodies, may hold the key to answering profound questions about where and how life could arise in environments vastly different from our own. The more we explore these chemical signatures, complex molecules embedded in the dust of distant worlds, the closer we come to unraveling the age-old question: are we alone in the universe? The presence of organic compounds scattered throughout space offers valuable insights into the geological and chemical makeup of asteroids, comets, and other celestial bodies. These compounds could even provide a window into the conditions that prevailed in the early days of our solar system, when Earth was still a molten ball of rock, slowly cooling and developing the atmosphere that would one day support life. Thus, the implications of finding organic compounds in space extend far beyond mere curiosity. They touch upon some of the most fundamental questions about life, the history of our planet, and the vastness of the cosmos that surrounds us. Each discovery moves us one step closer to understanding the origins of life and the possibilities of its existence elsewhere in the universe. As our exploration of space continues, we may begin to answer questions that humanity has pondered for centuries. One of the most fascinating areas of research in this quest is the search for microbial life beneath the icy shells of moons like Europa and Enceladus. These moons, orbiting the gas giants Jupiter and Saturn, are covered in thick layers of ice, beneath which lies vast oceans of liquid water. This combination of geological processes and the potential for biological activity creates an exciting and unique opportunity for scientists eager to explore the mysteries of life beyond Earth. From a geological perspective, understanding the structure and dynamics of the ice crust and the liquid ocean beneath is crucial. The surface features of these moons, such as cracks in the ice, geysers that expel water vapor, and the geological layers beneath the surface, offer key insights into the processes taking place within. For instance, plumes of water vapor and organic materials ejecting from the surface suggest that these subsurface environments may be active and rich in nutrients, potentially offering a hospitable environment for microbial life. By studying these geological features, scientists can identify possible habitats where life could thrive, effectively narrowing the search for potential microbial organisms. On the other hand, astrobiology, the study of the conditions necessary for life, plays a vital role in this investigation. Researchers are examining factors like the chemical composition of these oceans, the presence of energy sources such as heat or sunlight, and the possibility of metabolic processes that could sustain life. The chemistry of the materials spewing from the icy moons could reveal whether they contain the building blocks of life as we know it: carbon, hydrogen, oxygen, and other essential elements. By combining this astrobiological data with geological observations, scientists can assess the likelihood of microbial life existing in these extreme environments. This fusion of geological and astrobiological research represents a more holistic approach to understanding the potential for life beyond Earth. Missions like NASA's Europa Clipper and the European Space Agency's Jupiter Icy Moons Explorer are preparing to study these moons in unprecedented detail, gathering crucial data that could provide compelling evidence for microbial life. By examining the composition and behavior of these moons, these missions aim to answer one of the most profound questions of all: does life exist elsewhere in the solar system? In addition to the study of icy moons, space agencies worldwide are advancing a variety of innovative missions aimed at exploring other environments that might harbor life. Mars, for example, has long been a primary focus for researchers seeking evidence of past or present life. NASA's Perseverance rover, which has been tirelessly exploring the surface of the red planet, is gathering soil samples and searching for signs of ancient life. Equipped with sophisticated tools designed to analyze rocks for organic compounds, the rover is providing valuable insights into Mars's geological history and its potential to support life. Europa, one of Jupiter's many moons, is another key target in the search for extraterrestrial life. Beneath its thick icy crust lies an ocean that may possess the right conditions to support life. Upcoming missions, including NASA's Europa Clipper, aim to study the moon in greater detail, mapping the ice shell and investigating the potential for hydrothermal activity beneath the surface. This research could help scientists determine if Europa's ocean could indeed harbor microbial life. Venus, once thought to be a planet too harsh for life to exist, has recently emerged as a surprising contender in the search for extraterrestrial life. Studies of Venus's atmosphere have detected the presence of phosphine, a gas that on Earth is primarily produced by living organisms. This discovery has spurred interest in exploring Venus further. Proposed missions like NASA's Da Vinci Plus and Veritas aim to delve deeper into the planet's atmosphere and surface, potentially revealing signs of life in the clouds or in geological features on the surface. Finally, looking beyond our solar system, the James Webb Space Telescope has turned its gaze toward distant exoplanets, particularly those located in the habitable zone, the region around a star where conditions may be just right for life to exist. By analyzing the atmospheres of these distant worlds, scientists hope to detect biosignatures, chemical fingerprints left behind by living organisms. The search for life on exoplanets represents the next frontier in astrobiology, a quest that could ultimately reveal whether life exists beyond our home planet. Each of these missions is driven by hope and curiosity, bringing us ever closer to answering one of the most profound questions humanity has ever asked. Are we alone in the universe? Yet even as we explore these distant worlds, there remains another great mystery that continues to challenge our understanding of the cosmos: dark energy. Dark energy is one of the greatest puzzles in modern cosmology. It is a mysterious force that seems to be driving the accelerated expansion of the universe. Despite its profound influence on the cosmos, dark energy remains poorly understood, with several theories attempting to explain its nature. One of the most well-known theories is the cosmological constant, first proposed by Albert Einstein in the early 20th century. According to this theory, dark energy has a constant density that fills space uniformly, exerting a repulsive force that counteracts the gravitational pull of matter. This idea helps explain why galaxies are moving away from each other at an accelerating rate. However, while the cosmological constant fits well with observations, it raises some perplexing questions. One of the most puzzling aspects is why its value is so small compared to what physics predicts. Another intriguing possibility is the concept of quintessence, Unlike the cosmological constant, which assumes dark energy is constant, quintessence proposes that dark energy is dynamic and changes over time and space. Think of it as a fluid or field that evolves throughout the universe's history, influencing cosmic expansion in ways we are only beginning to understand. This flexibility could offer new insights into how dark energy interacts with matter and shapes the evolution of the universe. As we continue to explore the mysteries of the universe, whether by studying distant exoplanets, probing the icy moons of our solar system, or attempting to understand the enigmatic nature of dark energy, each discovery brings us closer to unraveling the profound truths about the cosmos. Through a combination of cutting-edge technology, innovative missions, and the unyielding curiosity of scientists around the world, we may one day find the answers to the age-old question of whether we are truly alone in the vast expanse of space. In recent years, a growing group of researchers has begun to venture into the realm of modifying the very foundation of general relativity itself. These bold alterations suggest that our understanding of gravity, especially at cosmic scales, may need a serious reevaluation. Rather than viewing gravity as an unchanging and constant force, some theorists propose that dark energy, a mysterious and pervasive force believed to be driving the accelerated expansion of the universe, might actually arise from deeper and more intricate laws of physics than previously imagined. These emerging theories offer fascinating and unique perspectives on the nature of the cosmos. As technology progresses, scientists continue to gather invaluable data through advanced observations, which could either confirm or challenge these theories. With each new breakthrough, we move closer to uncovering the enigmatic role of dark energy and its ultimate influence on the fate of the universe. One of the primary avenues for exploring this vast mystery lies in studying the effects of cosmic inflation, an extraordinary event that occurred in the earliest moments after the Big Bang. Cosmic inflation refers to an incredibly rapid and exponential expansion of the universe during the first fractions of a second after its inception. This event not only set the initial conditions for the universe as we know it, but also played a vital role in shaping the structure of the cosmos. To understand these early moments, scientists rely on a combination of observational techniques and advanced theoretical models. One of the most significant sources of data in this quest is the cosmic microwave background radiation, CMB, often described as the afterglow of the Big Bang. The CMB fills the entire universe, carrying subtle imprints from the time when the universe was merely a few 100,000 years old. It serves as a crucial relic from the infant universe, providing scientists with clues about its formation and evolution. Using sophisticated telescopes and instruments, researchers carefully measure tiny fluctuations in the radiation. These minute variations reveal how density differences in the early universe led to the formation of galaxies and large-scale cosmic structures. The intricate patterns found in the cosmic background radiation are key to unlocking the story of cosmic inflation and its impact on the universe's large-scale structure. Moreover, scientists have developed advanced models in which space self stretches and particles interact in highly complex ways. By simulating different scenarios of inflation, these models allow researchers to predict what the universe's large-scale structure should look like today. By comparing these predictions with actual observational data, a clearer picture emerges of how inflation set the stage for the cosmos we inhabit. But the exploration does not end there. Scientists are also delving into the detection of gravitational waves, ripples in the very fabric of space-time. The rapid expansion during inflation could have generated these waves, and detecting them would offer direct evidence supporting the inflationary theory. As technological advancements continue to progress, scientists remain hopeful that they will soon uncover more secrets of the universe's earliest moments, shedding light on the birth of the cosmos and our place within it. The universe operates through a delicate interplay of four fundamental forces: gravity, electromagnetism, the weak nuclear force, and the strong nuclear force. While the first three forces are well understood through the lens of quantum mechanics, gravity remains a puzzling anomaly. It is encapsulated in Einstein's theory of general relativity, which describes gravity as the curvature of spacetime caused by mass. Unlike the other three forces, which can be described within the framework of quantum mechanics, gravity remains an outlier, prompting profound questions about why it behaves so differently. One of the greatest unsolved mysteries lies in understanding gravity at the quantum level. Despite our understanding of gravity on macroscopic scales, such as how planets orbit stars or how objects fall to the ground, we lack a quantum theory of gravity that can seamlessly integrate with the rules governing the other fundamental forces. Current efforts to address this gap, such as string theory and loop quantum gravity, aim to provide a unified description of the forces. However, a complete and cohesive understanding remains elusive. These theories push the boundaries of our knowledge, yet the final answer is still out of reach, leaving physicists with more questions than answers. Another intriguing aspect of gravity is its remarkable weakness compared to the other fundamental forces. For example, a simple magnet can easily pick up a paperclip, but the gravitational forces between everyday objects are virtually imperceptible. To observe gravitational effects on a meaningful scale, we need massive objects like planets or stars. This vast difference in strength between gravity and the other forces raises important questions about the unseen realms of the universe. Could there be additional dimensions or even particles that we have not yet discovered, which could help explain the weakness of gravity? This disparity invites further exploration and challenges our current understanding of the fundamental forces. Compounding the mystery is the enigmatic presence of dark matter and dark energy. These elusive entities seem to exert a profound influence on gravitational behavior at the cosmic scale, yet they remain invisible and undetectable by traditional means. Together, dark matter and dark energy make up approximately 95% of the total mass energy content of the universe, yet they remain a complete mystery. Dark matter is thought to provide the unseen mass that helps galaxies and galaxy clusters hold together, while dark energy is believed to be responsible for the accelerated expansion of the universe. The quest to unravel the nature of these phenomena not only promises to broaden our understanding of the universe, but could also lead to groundbreaking advancements in physics. The search for answers to the riddles surrounding gravity, dark matter, and dark energy continues to captivate the minds of scientists, pushing the boundaries of what we know about the cosmos. Every new discovery opens up fresh avenues of inquiry, reminding us how much we still have to learn. These forces, though mysterious, are fundamental to the universe's structure and evolution. The pursuit of knowledge in this area is a testament to human curiosity, and it serves as a reminder of how much there is still to uncover in the vast, uncharted expanse of space. Entropy, a cornerstone concept in thermodynamics, is another key idea that plays a critical role in understanding the fate of the universe. In simple terms, entropy measures the amount of disorder or randomness in a system, and it is essential to grasp how the universe operates. In the context of stars, entropy is crucial to understanding the life cycles of these celestial bodies. Stars generate energy through nuclear fusion, which involves the transformation of lighter elements into heavier ones. This process, while increasing the complexity of the elements involved, also serves to decrease the overall entropy of the system, creating order from chaos. However, as stars reach the end of their life cycle, their ability to maintain this order diminishes, leading to an inevitable increase in entropy that shapes the star's ultimate fate. Thus, the study of entropy not only helps us understand the internal workings of stars, but also provides essential insights into the broader processes that govern the universe's evolution. As our understanding of entropy and its role in the cosmos deepens, we gain a clearer view of how stars form, evolve, and eventually succumb to the inevitable forces of decay. The ongoing exploration of these fundamental concepts is essential for constructing a more complete picture of the universe and its journey through time. However, over time, this cosmic process inevitably leads to an increase in entropy as energy is gradually dispersed into the universe in the form of light and heat. As stars burn through their nuclear fuel, they undergo profound transformations, ultimately resulting in various stellar remnants. These remnants, white dwarfs, neutron stars, or even black holes, represent significant markers of entropy's growth within the cosmos. For example, When a massive star collapses to form a black hole, its finely structured layers are obliterated, compressed into an incredibly dense point. Meanwhile, the surrounding material that falls into the black hole creates a chaotic environment, contributing to a greater increase in the overall entropy of the universe. On the grander scale of galactic evolution, the birth, life, and death of stars play a crucial role in shaping the structure and disorder of galaxies. Stars emerge in dense regions of gas and dust, creating an initial order in the universe. However, as stars go through their violent deaths, exploding in supernova or shedding their outer layers, they not only enrich the interstellar medium with new elements, but also inject a significant amount of disorder into the surrounding space. Over billions of years, gravitational interactions between galaxies and their eventual mergers lead to increasingly chaotic configurations. This process disrupts the earlier order, causing galaxies to lose their vibrant, star-forming regions and ultimately become dominated by dark matter. Looking ahead, as the stars continue to burn out and galactic interactions slow down, the universe is predicted to eventually approach a state of maximum entropy. In this distant future, the cosmos will be a vast, cold, and dark expanse, populated only by the remnants of stars and galaxies long past. The universe will reach a state of thermodynamic equilibrium, where everything drifts toward a stagnant, unchanging state. This scenario, often referred to as the heat death of the universe, underscores the fascinating interplay between entropy and the cosmic cycle of creation, transformation, and ultimate decay. One of the greatest challenges in understanding the universe involves measuring the curvature of space-time. The very concept of curvature itself is rooted in complex gravitational theories, most notably Einstein's general theory of relativity. According to Einstein, gravity is not a force, as traditionally thought, but rather the result of the bending or warping of space and time around massive objects. This geometric interpretation of gravity fundamentally reshapes our understanding of the cosmos and makes the measurement of space-time curvature a highly intricate task. The primary difficulty lies in the sheer scale and complexity involved in measuring space-time curvature. To gain an understanding of how space and time bend, scientists often rely on observations made across vast distances in deep space. When observing massive celestial bodies, such as black holes or neutron stars, we are essentially witnessing incredibly powerful warps in space-time. These objects bend light itself, a phenomenon known as gravitational lensing. While this effect provides valuable insights into the curvature of space-time, interpreting the data correctly requires sophisticated models capable of accounting for the shifting and dynamic nature of the cosmos. Instrumentation also plays a critical role in measuring space-time curvature. Many of the tools used to observe the universe rely on signals like light or gravitational waves, which can be influenced by a variety of factors as they travel across the cosmos. For example, when light passes near a massive object, its path is altered, causing it to appear as though it's diverging from a straight line. Scientists must carefully account for these deviations and ensure they do not confuse them with other cosmic events, such as supernova or gravitational ripples. This added complexity can introduce uncertainty into our measurements, clouding our understanding of space-time's true shape. Moreover, there is a conceptual challenge in how we perceive space-time itself. While we can measure distances and times independently, the interrelationship between these quantities in a curved geometry complicates our ability to create accurate models of reality. Physicists continue to refine theoretical frameworks and measurement techniques in an effort to better capture these intricate relationships, bringing us closer to a more precise understanding of the universe's fundamental structure. Each breakthrough we make in this area brings us closer to unlocking the mysteries of the cosmos. The discovery of the Higgs boson in 2012 marked a monumental milestone in our understanding of the universe and the nature of mass. At its core, the Higgs boson is the particle associated with the Higgs field, which permeates all of space. This field is fundamental because it is responsible for giving mass to elementary particles, allowing them to form the building blocks of the matter we observe. Without the Higgs mechanism, particles like electrons would remain massless, traveling at the speed of light and making the existence of a stable, structured universe impossible. Before this discovery, scientists struggled with numerous theories about why particles have the mass they do. The confirmation of the Higgs boson validated the standard model of particle physics, a framework that describes the fundamental forces and particles of the universe. The discovery of this particle at the Large Hadron Collider provided solid evidence for a theory that is not only simple but extraordinarily powerful in its ability to explain the workings of the universe. Furthermore, understanding the Higgs boson offers deep insights into the conditions of the early universe, just moments after the Big Bang. During this epoch, the universe was so hot and dense that particles had no mass. As the universe expanded and cooled, the Higgs field activated, granting mass to these particles and allowing the formation of atoms, stars, and galaxies. This tiny particle, therefore, holds a significant narrative about the origins of our cosmos. The implications of the Higgs boson extend far beyond the mass of elementary particles. It also invites questions about dark matter, gravity, and the fundamental forces that govern our universe. While much has been learned, there is still so much more to explore. This ongoing search for answers to the mysteries that lie beyond the Higgs field fuels the curiosity of scientists, driving them to probe deeper into the fundamental nature of the universe. It is this relentless pursuit of knowledge that continues to inspire cosmologists and enthusiasts alike, propelling humanity toward a deeper understanding of the cosmos. Meanwhile, the discovery of evidence for parallel universes could dramatically reshape our understanding of reality itself. The concept of parallel universes suggests that our universe may be only one of many, each with different configurations of matter, energy, and even the fundamental laws of physics. This revelation alone challenges our understanding of existence. If parallel universes exist, we could be just one small fragment in an infinitely vast cosmic tapestry, with countless other realities existing in parallel. One immediate implication of this idea concerns the nature of choice and consequence. Imagine a universe where every decision creates a branching path leading to a new reality. In one universe, you might have chosen a different career, while in another, you could be living an entirely different life. This idea resonates with age-old philosophical debates about fate and free will, suggesting that every possible outcome is realized somewhere in the vast multiverse. This raises exciting questions about identity and existence. Who are we, and what do our choices mean in the context of a far broader cosmic scale? The existence of parallel universes compels us to reconsider the fundamental nature of life, offering a new perspective on the relationship between our individual actions and the greater universe. The existence of parallel universes could unlock answers to some of the deepest and most perplexing mysteries in science. If proven true, it might provide fresh perspectives on some of the most unresolved questions in cosmology, such as the nature of dark matter and dark energy. These elusive substances remain invisible and yet essential to the structure of our universe, influencing galaxies and stars. But what if alternate universes, with their different properties and laws, could reveal why our own universe seems so finely tuned for life? Our universe, with its perfect balance of conditions that allow for galaxies, stars, and life, is a rare and fragile arrangement. If we discover that parallel universes exist, each one potentially harboring different physical laws or constants, we might finally be able to comprehend why our universe is the way it is. The question of why this universe could transform from an unsolvable riddle into a puzzle whose solution might lie in the vastness of the multiverse. Perhaps, through the study of these alternate realities, we could see our universe from a completely new angle, discovering that the characteristics we hold dear, such as gravity, the speed of light, or the abundance of matter, are not inevitable, but the result of cosmic luck or necessity within a far broader cosmic framework. Furthermore, the cultural implications of these discoveries would be far-reaching. If the existence of parallel universes were confirmed, it could profoundly influence art, literature, and philosophy. Human imagination is already stretching beyond the boundaries of what we know, envisioning vast, infinite worlds. New narratives would emerge, exploring what it means to be human in a limitless cosmos. Philosophers would be forced to reconsider our place in the universe, while artists might seek to capture the infinite possibilities of existence. These revelations could redefine our understanding of identity, purpose, and the very nature of reality, inspiring humanity to look inward and outward, asking new questions about the significance of our lives in an endless universe. In tandem with these concepts, the idea of time travel has sparked intrigue and speculation for centuries, captivating both scientists and storytellers alike. At its core, time travel theories challenge our perception of time as a constant, immutable force. Instead, they suggest that time is a dimension, intertwined with space, forming a flexible, malleable entity. This new understanding of time invites us to think about it in much the same way we perceive the dimensions of length, width, and height. Time is no longer a linear river we are carried along by, but rather a field of possibilities we might navigate, if only we had the right tools. Einstein's discovery of time dilation in the early 20th century was a monumental step forward in understanding how time behaves. It revealed that time doesn't pass at the same rate everywhere. Objects moving at high speeds, or those near massive gravitational sources like stars or black holes, experience time at a different rate than objects in less extreme conditions. This fundamental realization has opened the door to new scientific discussions about the nature of time, its relationship with space, and how it could potentially be manipulated. Could time travel, in theory, allow us to move backward or forward in time? And if so, what would the consequences be? The very possibility of traveling through time raises profound questions about causality, the relationship between cause and effect. If one could alter the past, would it create a ripple effect that changes the present or the future? This concept challenges our understanding of how events unfold, and it invites the possibility of multiple timelines, alternate realities, or even parallel universes that branch out from each decision or action. The more we contemplate these ideas, the more we are forced to think about the broader implications for the universe. How, if at all, might time affect the evolution of galaxies, stars, or the birth of life? What if time is more like a vast, complex tapestry, and each thread weaves together past, present, and future in ways we can barely begin to understand? Moreover, the study of time travel also forces us to think deeply about the very fabric of space-time. The movement of light through space is another example of how time and space are interwoven. When we observe light from distant galaxies, we are essentially looking into the past. This realization not only deepens our understanding of time itself, but also enhances our comprehension of cosmic phenomena, like the expansion of the universe. As we gaze across vast distances, we peer into the history of the cosmos, observing how it has changed over billions of years. For theorists, time travel represents a challenge to some of the most fundamental laws of physics. Traveling faster than light, a cornerstone of many time travel hypotheses, would require breaking the speed barrier, which seems impossible according to our current understanding of physics. However, as scientists continue to explore the limits of the universe, they uncover more about the underlying structure of reality, pushing the boundaries of what we believe to be possible. The deeper we dive into these concepts, the more we recognize how much we still have to learn, and how exciting the journey to understand time, space, and the cosmos truly is. In parallel with time travel, the discovery of new particles is another frontier in the pursuit of knowledge about our universe. Each new particle discovered represents a tiny piece of a vast cosmic puzzle, one that could radically alter our understanding of the laws that govern the universe. Just as a single missing puzzle piece can change the entire picture, new particles can refine existing theories or even give birth to entirely new ones. The discovery of the Higgs boson in 2012 is a prime example of how a single particle can reshape scientific paradigms. The Higgs boson confirmed the mechanism by which other particles acquire mass, a discovery that was central to the standard model of particle physics. This was not just another particle. It was a profound confirmation of the way the universe works at the most fundamental level. Yet, as significant as this discovery was, it was not the end of the journey. Every new particle discovered presents new questions. Some particles behave in unexpected ways, forcing scientists to re-examine their models of the universe. The possibility of dark matter, for example, has emerged largely from the behavior of particles that cannot be explained by current models. These unexpected discoveries open the door to entirely new areas of research. Concepts such as supersymmetry and dark matter, which once seemed speculative, are now legitimate areas of investigation, with the potential to rewrite the textbooks on cosmology and particle physics. The excitement of scientific discovery lies in this very uncertainty, the realization that every new piece of data brings with it the possibility of uncovering entirely new realms of reality. Whether these particles exist in parallel universes or form the building blocks of new physics, the journey of discovery continues to unfold, each revelation leading us closer to understanding the intricate and often mysterious forces that govern our universe. In the pursuit of knowledge, the most thrilling aspect of all is that there is so much left to explore. The universe, with all its mysteries, whether in the realm of parallel universes, time travel, or the smallest particles, remains a vast and untamed frontier. What we discover next will undoubtedly challenge our perceptions, expand our minds, and propel humanity further into the uncharted territories of the cosmos. Discoveries in the realm of particle physics frequently extend far beyond the boundaries of theoretical physics. These breakthroughs often spark technological innovations that resonate through various industries, impacting fields as diverse as medical imaging. Technologies developed to detect particles have revolutionized diagnostic methods, such as those used in scanning for diseases. Every new particle discovered brings with it not only an enhancement of our cosmic knowledge, but the potential for tangible applications that improve the quality of life for people around the world. Therefore, the search for new particles is far more than an academic pursuit. It is a journey that propels us towards deeper insights into the nature of the universe and catalyzes real-world innovations that benefit humanity. Similarly, the study of cosmic expansion holds immense significance, offering critical insights into the fate of the universe itself. When astronomers first began examining distant galaxies, they made a groundbreaking discovery. These galaxies were moving away from us. This realization, first proposed by Edwin Hubble in the early 20th century, shattered the long-standing belief that the universe was static. Hubble's work revealed a universe in motion, one that had likely originated from a hot, dense state and has been expanding ever since. This discovery revolutionized our understanding of the cosmos. As scientific research progressed, astronomers came to a startling conclusion. Not only was the universe expanding, but the rate at which it was expanding was accelerating. This unexpected development, first identified in the late 1990s through the observation of distant supernovae, introduced the enigmatic concept of dark energy. Dark energy, which permeates the universe, exerts a repulsive force that appears to be pushing galaxies apart at an ever-increasing rate, opposing the force of gravity. This phenomenon has become one of the most puzzling mysteries in modern science. Researchers are still working to unravel the nature of dark energy and its influence on the trajectory of the universe's evolution. The fate of the universe is intricately tied to the continued expansion of space. Several potential scenarios have emerged, each hinging on how dark energy behaves over time. One possibility is that the universe will expand forever, with galaxies gradually drifting apart over the course of trillions of years. As time passes, these galaxies could become isolated from one another, leading to a cold and dark universe, bereft of any meaningful cosmic interactions. Alternatively, if dark energy wanes or changes in nature, the expansion could slow down and ultimately reverse, pulling everything back together in a big crunch, a cataclysmic event where the entire universe collapses back into a singularity. However, the prevailing theory, supported by current observations, suggests that the universe will continue expanding indefinitely. This projection paints a picture of an ever-expanding, increasingly isolated cosmos, a universe that will grow colder and lonelier with the passage of time. As our understanding of dark energy continues to evolve, so too will our comprehension of the universe's ultimate fate. We are still in the early stages of uncovering the forces that govern cosmic expansion, and each new discovery brings us one step closer to understanding the true nature of the universe. The ongoing study of cosmic expansion serves as a reminder that the cosmos is full of secrets waiting to be unlocked, secrets that could change the way we view our place in the universe and our understanding of the forces that shape it. The quest to discover exoplanets, or planets that exist outside our solar system, is another awe-inspiring journey of scientific exploration that has spanned several decades. It all began in the 1980s when astronomers, including Geoffrey Marcy and his colleagues, began observing the movements of distant stars. They hypothesized that these stellar motions could be influenced by the gravitational pull of large planets orbiting them. While these early observations hinted at the presence of exoplanets, it wasn't until 1995 that the first confirmed exoplanet was discovered. Dubbed 51 Pegasi b, this gas giant, which shares many similarities with Jupiter, marked a monumental milestone in our understanding of the universe and ignited a wave of interest in the search for other distant worlds. The advent of more advanced technologies in the early 2000s significantly boosted the effort to detect exoplanets. In particular, space telescopes such as the Kepler Space Telescope, launched in 2009, played a pivotal role in this endeavor. Kepler's mission was to monitor thousands of stars simultaneously, observing subtle changes in their brightness caused by planets transiting in front of them. This technique, known as the transit method, allowed scientists to detect thousands of candidate exoplanets, significantly expanding our knowledge of these distant worlds. The data provided by Kepler not only revealed the existence of exoplanets, but also helped scientists gain insights into their size, composition, and orbits. As our detection methods improved, astronomers began to focus on a particularly intriguing category of exoplanets, those that might resemble Earth in certain key aspects. By the mid-2010s, the concept of the habitable zone emerged. This zone refers to the region around a star where conditions might be suitable for liquid water, a crucial ingredient for life as we know it. The discovery of exoplanets located in the habitable zone, coupled with advancements in technology, revealed that rocky planets potentially capable of supporting life existed beyond our solar system. By 2018, Kepler had confirmed the existence of over 2,000 exoplanets, further solidifying our understanding of the diversity of worlds that populate the galaxy. Today, the search for exoplanets is more intense than ever. With the launch of the James Webb Space Telescope in 2021, astronomers now have an even more powerful tool at their disposal. Webb's advanced instruments allow scientists to study the atmospheres of exoplanets in greater detail than ever before, potentially identifying signs of habitability or even life. The ongoing efforts to uncover the mysteries of exoplanets not only expand our knowledge of the cosmos, but also fundamentally alter our perspective on our place within it. As we continue to explore the farthest reaches of space, we are increasingly confronted with the possibility that we are not alone in the universe, and that the answers to some of the deepest questions about existence may lie on distant, unexplored worlds. The launch of the Hubble Space Telescope in the early 1990s represented another turning point in our understanding of the cosmos. Positioned far above the Earth's atmosphere, Hubble was able to capture images with unparalleled clarity and precision, free from the distortions caused by the Earth's atmosphere. This allowed the telescope to reveal the universe in ways that were previously unimaginable. One of Hubble's most significant contributions was its deep field images, where it focused on a tiny, seemingly empty patch of sky for an extended period. In doing so, Hubble uncovered thousands of galaxies, many of which were billions of light years away. These discoveries reshaped our view of the universe, showing us that it is far richer and more diverse than we had previously believed. The deep field images revealed galaxies of all shapes and sizes, from spiral to elliptical forms, highlighting the vast complexity of the universe. Hubble's observations have been instrumental in expanding our understanding of galaxy formation and evolution, providing key insights into the ways that galaxies interact and evolve over time. In summary, the discoveries made through the exploration of particle physics, cosmic expansion, exoplanets, and deep space observation have not only expanded our knowledge of the universe, but have also paved the way for technological innovations that impact our daily lives. As we continue to push the boundaries of scientific discovery, we remain on the precipice of even greater revelations that will shape our understanding of the cosmos and our place within it for generations to come. Moreover, Hubble played an indispensable role in measuring the universe's expansion rate, revealing groundbreaking insights about the cosmos. By observing distant supernovae, astronomers discovered not only that the universe was expanding, but that this expansion was accelerating at an alarming rate. This revolutionary finding led to the theory of dark energy, a mysterious force that constitutes the majority of the universe's energy content and is responsible for pushing galaxies further apart. This discovery fundamentally challenged long-standing scientific assumptions about the nature of cosmic dynamics. Hubble's observations transformed our perception of the universe from a static, unchanging entity to a dynamic, ever-expanding expanse, full of complexities. The telescope's awe-inspiring images and trailblazing discoveries ignited both public interest and scientific curiosity, reshaping how we think about galaxies and the vast cosmic landscape we inhabit. Through Hubble's lens, we continue to explore the mysteries of the cosmos, deepening our understanding of where we fit within the magnificent tapestry of the universe. The journey of cosmology is marked by remarkable breakthroughs that have continuously redefined our understanding of the universe. One of the most significant early milestones came in the 20th century with the work of Edwin Hubble. By analyzing the light emitted by distant galaxies, Hubble established that the universe is expanding. He observed that galaxies were moving away from us, with the more distant ones traveling at faster speeds. This realization shattered the previous belief that the universe was static and fixed, suggesting instead that space itself was stretching and growing. This finding dramatically reshaped our understanding of space and time. Following Hubble's revelations, the Big Bang theory gained widespread acceptance in the mid-20th century. This theory proposed that the universe originated from an infinitesimally small, incredibly hot point, approximately 13.8 billion years ago, and has been expanding ever since. In the 1960s, the discovery of cosmic microwave background radiation provided pivotal evidence supporting this theory. Researchers Arno Penzias and Robert Wilson serendipitously uncovered this faint, pervasive radiation while working on a satellite communication project. This afterglow, a remnant from the universe's early stages, confirmed the Big Bang theory and offered a snapshot of the universe's infancy. In the latter half of the 20th century, the concepts of dark matter and dark energy came to the forefront of cosmological research. Observations showed that galaxies were rotating at speeds that couldn't be accounted for by visible matter alone. This led to the proposal that a mysterious form of invisible matter, dark matter, permeates the universe, exerting gravitational forces that affect the motion of galaxies. Alongside dark matter, the discovery of the universe's accelerating expansion in the 1990s introduced the concept of dark energy, a force that propels this rapid expansion. Together, dark matter and dark energy account for a staggering 96% of the universe, even though we have yet to observe them directly. These groundbreaking discoveries not only provide a framework for understanding the structure and evolution of the universe, but they also open the door to questions that remain beyond our current grasp. Each revelation invites new inquiries, suggesting that the cosmos is far more mysterious than we can fathom. As our scientific probes delve deeper into the universe, who knows what astonishing discoveries lie just beyond our reach. Among the most compelling pieces of evidence supporting the Big Bang theory is the discovery of the cosmic microwave background, CMB radiation. This faint, omnipresent glow fills the entire universe, a relic from a time when the cosmos was dense, hot, and turbulent. The CMB serves as a time capsule from the universe's early stages, revealing crucial information about its origins. First detected in the 1960s by Arno Penzias and Robert Wilson, the CMB appeared as an unexpected noise coming from every direction in the sky. After ruling out local sources of interference, they realized that they had stumbled upon the afterglow of the Big Bang itself. This radiation is remarkably uniform, with tiny fluctuations that offer clues about the formation of the first galaxies and cosmic structures. These fluctuations represent the seeds from which galaxies, clusters, and larger structures would eventually form. The CMB's temperature, measured at about 2.7 degrees above absolute zero, provides additional confirmation of the Big Bang model. This cooling of the universe since its fiery beginning reflects the overall expansion of space. As the universe expanded, it cooled, and light was able to travel freely through space, allowing the cosmos to become transparent. The CMB thus acts as a snapshot of the universe's infancy, providing a glimpse into its state nearly 14 billion years ago. The discovery of the CMB not only validated the Big Bang Theory, but also opened new avenues for understanding the universe's history and evolution. It gave scientists a tangible piece of evidence that the universe's expansion was both real and observable, providing a foundational tool for cosmological studies. Another major advancement in cosmology came with the detection of gravitational waves in 2015. These ripples in space-time, first observed by the LIGO Observatory, revolutionized our understanding of the universe by offering a completely new way of observing celestial events. Gravitational waves allow us to study cosmic phenomena that were previously invisible to traditional telescopes, which rely on electromagnetic radiation such as light or radio waves. These waves, produced by catastrophic events like black hole mergers or neutron-star collisions, carry information about their origins that is often hidden from our view. For example, when two black holes spiral towards each other and eventually merge, they emit gravitational waves that reveal critical information about the masses and spins of the black holes involved. This discovery not only provides new insight into the most extreme environments in the universe, but it also allows us to study the fundamental properties of gravity, a force that governs much of the cosmos. By observing gravitational waves, scientists can peer into regions where gravity is at its strongest and gain valuable insights into the behavior of matter under the most extreme conditions. This opens up a new realm of inquiry into the fundamental nature of space, time, and the forces that shape the universe. In doing so, it deepens our understanding of Einstein's theory of relativity and continues to challenge and refine our views on the fabric of reality itself. Each of these discoveries, from Hubble's observations to the detection of gravitational waves, has reshaped our understanding of the universe and our place within it. They serve as a reminder that the cosmos is a realm of infinite mystery, where each new discovery only opens the door to further questions. As science advances and our technology improves, we continue to uncover the secrets of the universe, inching ever closer to understanding the full scope of the cosmos. What lies ahead in this uncharted territory is a future filled with limitless possibilities, and with each discovery, we draw nearer to the ultimate truths about the universe we call home. The detection of gravitational waves has not only marked a monumental technological breakthrough, but also ignited the birth of an entirely new scientific field: gravitational wave astronomy. This emerging discipline has opened a window into the most violent and energetic events in the universe, events that were once beyond the reach of traditional observational methods. Gravitational waves, ripples in the very fabric of space-time caused by massive cosmic phenomena such as colliding black holes and neutron stars, allow scientists to observe these cataclysmic occurrences in real time. What makes this field particularly captivating is its ability to offer a multisensory view of the cosmos. When gravitational waves are detected, astronomers are able to turn their telescopes to the same region of space and observe other forms of electromagnetic radiation, such as visible light, gamma rays, and X-rays, that are emitted by these powerful cosmic events. This approach, known as multi-messenger astronomy, brings together data from various wavelengths, enabling a more holistic understanding of phenomena that were previously only understood in part. The combined observations paint a more complete and nuanced picture of the universe's most catastrophic events, linking them across different cosmic scales and phenomena. This convergence of multiple forms of observation is a game changer. It not only provides scientists with richer, more detailed insights, but also allows for the cross-validation of findings, which makes the data more robust. In this way, gravitational wave astronomy isn't merely a technological leap. It signals the beginning of a new era in our quest to unravel the mysteries of the universe. As more waves are detected and technology advances, we are poised to uncover astonishing revelations about the very nature of black holes, neutron stars, and even the structure of space-time itself. With every new discovery, the horizons of our cosmic knowledge expand, pushing the boundaries of human understanding farther than ever before. This journey into the cosmos, however, is not a recent development. The history of celestial mechanics, the branch of astronomy that deals with the motions of celestial bodies, spans centuries, marked by the contributions of brilliant minds that helped shape our understanding of how the universe operates. One of the earliest figures in this story is Johannes Kepler, a German mathematician and astronomer who, in the early 17th century, made pivotal strides in our understanding of planetary motion. Kepler's formulation of the laws of planetary motion demonstrated that planets do not orbit the sun in perfect circles, as had been believed for centuries, but in ellipses. This discovery forever altered our understanding of the solar system and set the stage for later breakthroughs in celestial mechanics. While Kepler's insights were groundbreaking, they would not have been possible without the work of Isaac Newton, whose theories would revolutionize science. In the late 17th century, Newton introduced the law of universal gravitation, proposing that every mass in the universe exerts an attractive force on every other mass. This idea was revolutionary. It not only explained the motion of planets, but also accounted for the motion of everyday objects on Earth. Newton's mathematical framework provided the key to understanding the forces that govern the universe and laid the foundation for the science of celestial mechanics as we know it today. Another key figure in the development of celestial mechanics was Pierre-Simon Laplace, an 18th century French mathematician who expanded upon Newton's work. Laplace's 5-volume Mécanique Céleste, Celestial Mechanics, introduced new mathematical techniques that allowed astronomers to solve more complex problems concerning the motions of celestial bodies. His work helped to clarify the stability of the solar system and provided deep insights into the gravitational interactions between planets. Laplace's theories would influence the field for generations, shaping the work of future astronomers and mathematicians. In the 19th century, Carl Friedrich Gauss refined celestial mechanics even further with his work on the mathematics of orbits and his application of statistics to predict the movements of celestial bodies. His contributions were critical to improving the accuracy of orbital predictions, paving the way for future explorations of the solar system and beyond. These remarkable scientists, Kepler, Newton, Laplace, and Gauss, each made invaluable contributions that transformed our understanding of the cosmos. Through their collective efforts, the study of celestial bodies went from speculative philosophy to a rigorous, empirical science. Their work revealed the intricate dance of planets, moons, and stars, fundamentally altering our perception of our place in the universe. These advancements were built on the observations of ancient civilizations, such as the Babylonians, who carefully documented the movements of stars and planets, though their geocentric models saw the Earth as the center of the universe. The Babylonians' observations were among the earliest recorded efforts to understand the cosmos, and their early astronomical calendars helped predict celestial events. However, their models of the universe, where the planets moved in circular orbits around the Earth, eventually gave way to the more refined ideas of Greek philosophers. Claudius Ptolemy, for example, proposed a complex geocentric model in the 2nd century known as the Ptolemaic system. His model accounted for the observed motions of the planets through a series of nested circles called epicycles. Though Ptolemy's system dominated Western thought for over a millennium, it became increasingly complicated as more accurate observations were made, leading to growing inconsistencies with the data. The true revolution in our understanding of the universe came with the work of Nicolaus Copernicus in the 16th century. Copernicus proposed a heliocentric model, placing the sun at the center of the solar system instead of the Earth. This radical shift simplified the explanation of planetary motion and aligned it with the observed motions of celestial bodies. Though initially met with resistance, Copernicus's ideas set the stage for future advancements in astronomy. Building on Copernicus's ideas, Johannes Kepler, using the meticulous observational data of Tycho Brahe, further refined our understanding of planetary motion. Kepler's laws of planetary motion demonstrated that planets move in elliptical orbits, a concept that had never been considered before. This new understanding paved the way for Isaac Newton's law of universal gravitation, which would ultimately unify Kepler's laws with a deeper, more comprehensive understanding of the forces at play in the universe. The history of early astronomy thus unfolded as a gradual yet profound evolution from ancient observations to modern scientific rigor. It transformed our understanding of planetary motion, turning it from an abstract philosophical idea into a precise and predictive science. A more recent leap in our understanding of the cosmos came with the Kepler mission, launched in 2009. Kepler's primary goal was to search for exoplanets, planets orbiting stars outside our solar system, and it succeeded spectacularly. Using the transit method, Kepler detected the dimming of stars as planets passed in front of them. This led to the discovery of over 2,000 exoplanets, many of which reside in what is known as the habitable zone, where conditions might support life as we know it. Kepler's discoveries revealed a stunning diversity of planetary systems, vastly different from our own. It uncovered systems with multiple planets packed closely together, gas giants orbiting near their stars, and planets resembling Earth in both size and composition. These findings expanded our understanding of how planetary systems form and evolve over time. More importantly, the data suggested that Earth-like planets may be common in the galaxy, potentially leading to billions of habitable worlds in the Milky Way alone. Kepler's work also spurred renewed interest in the search for extraterrestrial life, prompting scientists to explore what conditions are necessary for life to emerge. The Kepler mission has reshaped our view of the cosmos, underscoring the uniqueness of Earth, while also suggesting that we may not be alone in the universe. Technological advancements in space exploration have played a key role in transforming our understanding of the universe. From the invention of the telescope in the early 17th century to today's sophisticated observatories, each technological leap has opened new windows into the cosmos. Modern telescopes equipped with high-resolution cameras and sensitive detectors allow us to capture breathtaking images of distant stars and galaxies, revealing wonders previously unseen. Space missions like the Voyager probes have expanded our reach beyond the solar system, sending back invaluable data from distant planets, moons, and even interstellar space. These missions have not only enhanced our knowledge of the cosmos, but also captured the imagination of humanity, showing us that the universe is full of mysteries, just waiting to be explored. Additionally, advances in computer technology and data analysis have revolutionized the way we study the universe. With the vast amounts of data produced by telescopes and space missions, advanced algorithms and artificial intelligence now play an essential role in processing this information. These technologies help scientists identify patterns and make groundbreaking discoveries that would have been nearly impossible to achieve manually. By simulating cosmic events and modeling the complexities of the universe, we are now able to explore the cosmos with unprecedented detail and accuracy. As we continue to explore and study the vastness of the universe, the journey is far from over. Each new discovery, each breakthrough in technology brings us one step closer to understanding the mysteries of space, time, and the forces that govern the universe. The pursuit of knowledge, driven by both human curiosity and ingenuity, will continue to propel us forward, unveiling even more wonders of the cosmos in the years to come. Technology has opened new frontiers in global collaboration, bringing scientists from every corner of the world into an unprecedented network of real-time communication. This interconnected world has significantly accelerated the pace of research and discovery, enabling knowledge to be shared instantly across continents. Whether through international satellite networks or online research journals, scientists can now collaborate and contribute to the collective wealth of human understanding. This exchange of information has cultivated a dynamic, interconnected scientific community that continues to push the boundaries of what we know. As technology advances further, so too will our capacity to explore and understand the universe, ensuring that the quest for knowledge remains a fascinating and ever-evolving journey for future generations. Throughout the ages, artifacts have played a pivotal role in expanding our comprehension of celestial events, particularly eclipses. Ancient civilizations, captivated by the movements of the sun and moon, left behind invaluable records, both written and physical. that provide profound insights into their interpretations of these cosmic phenomena. One of the earliest and most notable examples comes from Babylon, where astronomers meticulously documented lunar and solar eclipses on clay tablets. These records did more than just track the occurrence of these celestial events. They also laid the groundwork for the development of predictive techniques that could forecast future eclipses with remarkable accuracy. These early efforts marked a significant leap in humanity's ability to observe and anticipate the cosmos. The ancient Greeks, highly attuned to the patterns of the heavens, were keen users of these Babylonian records. Thinkers like Anaxagoras and later astronomers in Greece found great value in the Babylonian insights. Using simple yet effective tools such as gnomons, vertical sticks that cast shadows, they measured the angles of the sun, deepening their understanding of solar and lunar phenomena. These early tools and methods provided the Greeks with a foundation for the astronomical theories they would later develop, enhancing their narratives about celestial movements. In this way, the Babylonian records were crucial in shaping the path of Greek astronomy and their growing understanding of the cosmos. The Mayan civilization, too, made significant contributions to the study of celestial bodies. Known for their sophisticated calendar systems, the Maya didn't just track the movements of the sun, moon, and planets. They built monumental structures precisely aligned with astronomical events like eclipses. Their codices, filled with detailed predictions of these events, underscore the central role celestial phenomena played in their culture and religion. The Maya's meticulous observations and integration of celestial events into their societal frameworks highlight their advanced understanding of the cosmos. Modern-day researchers piecing together these ancient records have uncovered not only the mechanics behind solar and lunar eclipses, but also the deep cultural significance they held for these civilizations. Each of these ancient artifacts, whether clay tablets from Babylon or codices from the Maya, has helped build a timeline of humanity's understanding of celestial events. These records are windows into how ancient societies viewed the heavens, offering us a glimpse into our long-standing curiosity and thirst for knowledge about the universe. From these humble beginnings, humanity's journey of exploration has blossomed into the sophisticated scientific endeavors we see today. As we continue to look to the stars, a number of upcoming space missions hold great promise for further expanding our understanding of the cosmos. One of the most highly anticipated is the James Webb Space Telescope, JWST, slated for launch in the near future. With its advanced capabilities, JWST will observe the universe in infrared light, allowing it to peer through cosmic dust and gas clouds to study the birth of stars and galaxies. It will also examine the atmospheres of distant exoplanets, potentially uncovering conditions that could support life beyond our planet. JWST's groundbreaking technology will provide a detailed view of the universe's earliest moments, offering unparalleled insight into its formation. Another exciting mission is the European Space Agency's Euclid mission, set to launch shortly. This mission is dedicated to studying the mysteries of dark energy and dark matter, two of the most elusive and fundamental components of the universe. Euclid will map the geometry of the universe by observing billions of galaxies across vast stretches of time, using shifts in light to uncover the hidden forces that shape the cosmos. With this mission, astronomers hope to answer profound questions about gravity and the fundamental structure of the universe. NASA's Lunar Gateway is another groundbreaking venture. This planned outpost orbiting the moon promises to enhance our exploration of lunar resources while serving as a springboard for future human missions to Mars. The Lunar Gateway will not only contribute to scientific research on the moon, but will also help astronomers better understand how the moon influences Earth's environment, deepening our knowledge of celestial phenomena closer to home. Lastly, the Chinese Space Telescope, known as Sunan, is poised to complement the work of both the Hubble and James Webb telescopes. Sunan aims to provide high-resolution images of the universe and survey vast areas of the sky, potentially uncovering new astronomical phenomena. With its unique capabilities, Sunan may offer groundbreaking insights into how galaxies evolve over time, contributing to our understanding of the universe's past, present, and future. Together, these missions represent a new era of space exploration, each promising to illuminate previously hidden aspects of the cosmos. From the study of exoplanets to the mysteries of dark matter, they are poised to expand our understanding of the universe in profound ways. As we embark on this next chapter of cosmic exploration, the future of astronomy is brimming with possibilities. The technological advancements in telescope design have revolutionized our ability to observe distant galaxies. Through constant innovations, telescopes are now capable of peering deeper into the cosmos than ever before. The core of these improvements lies in enhancing the instrument's light-gathering capabilities, improving resolution, and expanding the range of wavelengths that can be observed. As the universe is vast and often cloaked in darkness, the ability to capture faint light from distant objects is crucial for uncovering their structure, composition, and history. Modern telescopes are equipped with sophisticated mirrors and lenses that capture far more light than their predecessors. Larger apertures allow these instruments to gather signals from galaxies billions of light years away, uncovering details previously hidden in the darkness. For instance, the James Webb Space Telescope, with its expansive mirror, far surpasses traditional telescopes by capturing infrared light. This capability opens up new avenues for exploring the formation of stars and planetary systems, which may be obscured by clouds of gas and dust. Further enhancing our observational capabilities, advancements in adaptive optics technology have allowed astronomers to achieve unprecedented clarity in their images. This technology helps to counteract the distortions caused by Earth's atmosphere by using flexible mirrors that adjust in real time, correcting for atmospheric turbulence. With this improvement, astronomers can observe distant galaxies with remarkable sharpness, revealing intricate details that would have been lost in earlier observations. As technology continues to evolve, these advancements promise to unlock even more of the universe's secrets, bringing us closer than ever to understanding the vast and mysterious cosmos that surrounds us. The integration of advanced digital technologies and cutting-edge data processing techniques has fundamentally reshaped our approach to understanding the cosmos. These tools, empowered by powerful computational algorithms, enable scientists to sift through the immense volume of data collected by modern telescopes. The sheer scale of information gathered from distant galaxies, nebulous clouds, and star-forming regions would be insurmountable without such technology. Thanks to these innovations, researchers can now draw meaningful, precise conclusions about the structure, age, and behavior of these faraway celestial bodies. This fusion of enhanced hardware and pioneering software doesn't simply represent a leap forward. It marks a monumental shift in our cosmic exploration. With the advent of these advancements, we have taken a giant stride into the universe, unlocking secrets of distant galaxies that were once beyond our grasp. One of the most groundbreaking instruments at the heart of this revolution is the James Webb Space Telescope, launched in December 2021. This remarkable observatory is pushing the boundaries of what we know, going far beyond the capabilities of its predecessor, the Hubble Space Telescope. At its core, the James Webb Space Telescope was designed to observe the universe in the infrared spectrum, a crucial ability that allows it to peer through dense clouds of cosmic dust and gas. These clouds had previously obscured our view of distant star-forming regions and galaxies. But now, with Webb's advanced infrared sensors, we can examine these objects in unprecedented detail. Webb's infrared vision allows us to see the formation of stars, the birth of galaxies, and other cosmic phenomena that had once been hidden from our view. One of the telescope's most exciting capabilities is its ability to look back in time, specifically to a period just a few hundred million years after the Big Bang. During this epoch, the universe was in its infancy, and Webb's ability to observe these early moments could provide answers to fundamental questions about the origins of the cosmos. This unprecedented capability gives scientists the opportunity to examine celestial objects that formed during this critical period, shedding light on the processes that led to the creation of the first galaxies, stars, and black holes. These early formations are key to understanding the larger framework of cosmic evolution. In addition to its contributions to cosmology, the James Webb Space Telescope plays a crucial role in the search for exoplanets, planets located outside of our solar system. Its sophisticated spectroscopic instruments allow scientists to study the atmospheres of these distant worlds, searching for chemical signatures such as water, methane, and even the basic building blocks of life. This is an exciting frontier in astrobiology, as Webb's observations could provide clues about whether certain exoplanets may harbor life or could be suitable for life in the future. By analyzing these distant worlds, Webb helps expand the conversation about the possibility of life beyond Earth. The telescope's significance also extends to our understanding of stellar life cycles. Through its detailed observations of the birth, life, and death of stars, Webb enables scientists to explore the different stages of stellar evolution. This deepens our understanding of how stars form, how they evolve, and how they eventually explode in dramatic supernovae. More importantly, studying these processes helps us understand how elements are created and distributed throughout the universe. These elements, the building blocks of planets and life itself, are integral to our understanding of how our own solar system came to be. As we look toward the future, several upcoming astronomical surveys promise to push the boundaries of our understanding even further, particularly in the realms of dark matter and dark energy. These two mysterious and largely unseen forces are believed to make up most of the universe's mass and energy, yet they remain largely unexplored. One of the most eagerly anticipated projects is the Vera C. Rubin Observatory in Chile. This observatory, with its ambitious legacy survey of space and time, will conduct a 10-year survey of the night sky. The data it captures, focusing on the brightness and movement of billions of stars and galaxies, will help unravel the enigma of dark matter and its effects on the formation of cosmic structures. Another groundbreaking mission is the European Space Agency's Euclid mission, which is set to launch in the near future. Euclid will map the large-scale structure of the universe using advanced imaging techniques. By observing the way galaxies are distributed and how their light is bent by gravity, Euclid will provide critical insights into the nature of dark matter and the accelerated expansion of the universe, which is thought to be driven by dark energy. With its precise measurements, Euclid promises to test various theories about these elusive components and their roles in the evolution of the cosmos. In South Africa, the Meerkat radio telescope, part of the larger Square Kilometre Array project, is poised to provide new perspectives on the universe. This observatory aims to create detailed three-dimensional maps of galaxies, helping scientists explore the unseen forces at play, particularly the role dark matter plays in shaping the structure of the universe. By observing how galaxies interact and evolve, the project will offer crucial insights into the fundamental forces that govern the cosmos. Finally, NASA's Wide Field Infrared Survey Telescope, WF-IRST, will survey vast regions of the sky in infrared light. Its primary goal is to explore the expansion of the universe while also capturing data on the distribution and behavior of dark matter and dark energy. This mission will add another crucial piece to the puzzle of understanding the universe's composition and its mysterious forces. Together, these surveys and missions represent a concerted effort to deepen our understanding of the universe. Each project, with its unique methodologies and technologies, will contribute to a more comprehensive picture of the cosmos, potentially bringing us closer to uncovering the secrets of dark matter and dark energy. As these projects unfold, they will expand the boundaries of our cosmic horizons and may even revolutionize our understanding of the universe itself. In parallel, missions focused on exploring the outer solar system are poised to uncover profound insights into planetary science and the origins of life. Celestial bodies such as Europa and Enceladus, moons encased in thick layers of ice, have long intrigued scientists. Beneath their frozen exteriors, vast subsurface oceans may exist, oceans that could harbor the ingredients necessary for life, or perhaps even life itself. These moons offer a unique opportunity to study the conditions that could support life in other parts of the universe. By investigating the chemical composition of the oceans beneath the ice, scientists may find similarities to the primordial Earth or environments on exoplanets. This research holds the potential to not only expand our understanding of astrophysical processes, but also provide a glimpse into the conditions that could foster life elsewhere in the cosmos. Moreover, studying these icy worlds is crucial for understanding the history of our own solar system. These moons are thought to preserve ancient material from the early solar nebula, essentially acting as time capsules. By analyzing the surface and subsurface materials of these moons, researchers can learn more about the conditions that existed when our solar system was forming, offering new insights into how planets and moons came into existence. The technological challenges of exploring these distant, frozen worlds are immense, but they drive innovation in spacecraft design and robotic exploration techniques. As these missions progress, they will not only advance our scientific knowledge, but also inspire wonder about our place in the cosmos. The icy bodies of the outer solar system are not just remote destinations, they are keys to unlocking some of the greatest mysteries of the universe itself.